Hey everyone, today we are going to be implementing the entirety of the transformer architecture with absolutely no PyTorch. This means we need to implement both the forward pass and the backward pass for all the different operations we care about. And there are two reasons for this. One, it gives you a deeper understanding, of course, of what's going on internally because, well, PyTorch kind of does a lot of that heavy lifting for you, right? We just define a function, it takes the derivative, and we're all happy. Number two is it's a precursor to the MyTorch architecture that I'm currently working on and will be making videos on to actually make a fully functioning deep learning framework, and we'll see some of those details a little bit later. For now though, let's just keep going and understand in a neural network, what are the pieces that go into it? Neural networks are basically just a sequence of operations, right? And in PyTorch, we define these operations, right? You have nn.linear, nn.conv, whatever it may be. We just define all these operations. You can even define your own custom functions, right? You can take something, you can take the sign of it and then square it or do whatever, right? Anything you want, you can do. And we just define these operations and that's it. That's all we do in PyTorch. And the reason that's all we have to do in PyTorch is because Autograd will go ahead and compute the derivatives for us. As long as the functions we define are basically a sequence of known operations, things that PyTorch already has defined, then it's good to go. It can use those smaller known operations to compute our actual operations derivative with chain rule. And an example of this, the one I really like typically, is the sigmoid function. Because sigmoid, this 1 over 1 plus e to the negative x, well, there's actually a bunch of functions that go into this, right? So we can break this up. We can say a is negative x, so it's taking our input x, multiplying by -1. And then b takes a and exponentiates it, right? E to the power a. And then c takes that value and adds 1 to it. And then d takes the reciprocal. Now, how do I compute the chain rule between all of this? Well, it's easy. If we do, let's make this pencil so much smaller. 1 second. So if we do dc times dc db, and then db dA, and then dA dx, right? This is just chain rule, right? I can take I know what dc is, right? The derivative of this. I know the derivative of what a reciprocal is. I know what the derivative of 1 plus something is. I know what the derivative of e to the power something is. And I know what the derivative of -1 times something is. So if I multiply all of those things together, I will get effectively the same derivative as this, right? Because again, this is just chain rule. There's nothing else going on. We'll see in a second why this is typically not a good idea. And so let's just keep going. The end goal of this, not today's video, but of many videos, is to build a fully functioning deep learning framework. And deep learning frameworks just need a couple of things to make them work well. One, we need to somehow define an array, right? And these arrays will work on GPU or CPU, whatever it may be, and we'll be using Cupy and Numpy to do this. If you've never heard of Cupy before, it's exactly Numpy. It's just Numpy on GPU. So it makes our life a little bit easier. And then these arrays will be wrapped in some tensor logic, and the tensor is the thing that does our automatic differentiation, right? Keeps track of stuff and takes derivative. We'll see all that later. Then with these tensors, we can perform some operations, right? We can add, we can multiply, divide, subtract, exponentiate, whatever, right? All sorts of operations that we can do, and we'll see a whole, a laundry list of operations we'll want to support when building a deep learning framework. And then these operations are a part of some modules, right? And the modules are the things we really care about, the linear layers, the layer normalizations, the convolutions, the attention, all that sort of stuff. But modules come in two different types. We can have modules that are custom, right? We can define our own modules. And if we define our own modules, then the Autograd mechanism should be able to compute the derivatives of them. But then there's also modules that I know everything about. Modules that I define, linear layers or LayerNorm or ReLU or anything that I define. I know what the input and the output is. I know what the derivative should be, so we can manually define those derivatives. We'll see the benefit of that in a bit. The main goal, though, is we can then write fused Triton kernels to make our GPUs scream, right? It'll go way, way faster. We'll see all of the benefits of this much in the future. And then, of course, any reasonable deep learning framework would be able to train on multiple GPUs in mixed precision. So we'll be implementing all of that stuff in the future as well. This is an active project. You can go on my Git repo. I'll link it down below. You can already try it out. I'm working on making a Colab notebook right now just to make life a little bit simpler so everyone can use it. But let's just go ahead and keep going, right? Because for us to enjoy the benefits of Autograd, we first need to suffer through ManualGrad, right? Manually defining all the derivatives. And ManualGrad is going to show up again when we define the kernels in the future. So we'll see all of that. So why do we care about ManualGrad? So going back to our sigmoid function, sigmoid is, again, we take some input, we multiply it by -1, exponentiate it, add 1, take the reciprocal. This means for us to do backpropagation, well, do dz, dz dy, dy dx, dx dw, and we'd have to kind of go back, through this chain of operations. The problem is this: if I want to compute do dz, right, and the function is 1 over z, then derivative of O with respect to z is -1 over z squared, right? Standard setup for derivatives of a fraction. Well, I need z. For me to compute -1 over z squared, I need z. But that means I need to store z in memory, right? Because in the forward pass, I'm going to produce all of these outputs, but in the backward pass, for me to do the backward pass, I need z. I need y here to compute the backward pass. I need x here to compute the backward pass, ... And so this is something just to keep in mind when doing Autograd. Autograd has the convenience that, yes, it will do all of this for you, but the memory cost is higher because all of these intermediate outputs need to be stored for backward pass to be successful. So what if it's a known composite of operations? I know what the derivative of a sigmoid is, right? I know that do dw is just the sigmoid of w times 1 minus the sigmoid of w, right? Or the output times 1 minus the output. I already know that. So I could just skip all of that work and just circumvent it because I don't really care about the intermediate values here or what the intermediate derivatives are. I just want the derivative of the output with respect to the input. And in that case, if I know exactly what it should be, then why not just go ahead and define it, right? Saves us a ton of time, ton of memory, ton of compute, and doing O times 1 minus O is a significantly simpler computation than doing -1 over z squared times 1 times e to the x times negative, right? This is ridiculous, right? We want to avoid this as much as possible. And so this is why manually defining gradients is so important. Here's just a quick example, right? For the sigmoid, this is not code we'll be writing today, but just code we will be writing in the future. And you can see that if we have done it this way, this is if we use full Autograd will go ahead and, we have exponentiation, we have -1, we have summation, we have a reciprocal. All of these operations are implemented in the tensor to do our backward pass, right? So it will essentially do what we saw in this figure here. It'll just kind of do this backward pass as it goes. On the other hand, if we know that we're doing a sigmoid, then we're better off just defining it this way. I know that the derivative is the output times the 1 minus output. So I shouldn't be wasting all of this compute here. We can just define the backward manually here. And this is exactly one of the tricks that PyTorch does that makes it so efficient. It uses Autograd for stuff that I define, right? Stuff that I define, it'll just automatically differentiate and it's good to go. But for stuff that it already knows, if we call sigmoid in PyTorch, PyTorch knows exactly what a sigmoid is. It's not going to waste time backpropagating through sigmoid. It's going to use a more efficient way, right? It knows what the derivative of sigmoid is, so let's just go ahead and do that directly. We don't need to go through that Autograd step. You can do this, right? You can define sigmoid like this in PyTorch. It's just wasted compute, right? We don't need to backpropagate through this stuff. And so let's kind of understand what backpropagation is before we keep going, right? And so here's an example. We have some input x. We're going to do a matrix multiplication with w and then add a b. So this is essentially y is going to be x w plus b, right? Standard linear layer, nothing fancy. And then y is going to be our output. It's going to go to some loss function, right? Mean squared error, cross entropy, whatever it may be. And in backpropagation, our goal is to update w and b. These are the learnable parameters in this system that we want to, optimize. Optimize w and b such that we minimize the loss. And the way we do that is we want to compute the derivative of the loss with respect to b, and the derivative of the loss with respect to w. And the derivative tells me that if I increase w by this much, then L will increase by this much. If I decrease w by this much, L will decrease by this much. And we want to move w and b in the direction opposite of the gradient, right? We want to minimize our loss. And so to do that, it's very simple. If I want dl/db, well, the loss came from y, so we have to do dl/dy, and then dy/db, standard chain rule, right? dl/dy, dy/db, and that will give me dl/db in the end, right? My derivative of the loss with respect to b. And then similarly, if I want dl/dw, then I have to do dl/dy, dy/da, right? So a is my temporary output that I added b to, and then da/dw, right? da/dw. So dl/dy, dy/da, da/dw is just dl/dw, dl/dw. And that's it, right? So that gives me my derivatives, and I can use these derivatives to update my weights and biases. And it's as simple as that. Now, of course, this is an example of just one linear layer, right? It's just we have some input, we do some matrix multiplication, we add b, and we're good to go. What if we have two, right? Deeper models, typically we have multiple linear layers. Well, that's easy enough. Same idea, dl, dy, dy, db. And in this case, we have a b2 and a w2 for the second linear layer, and a b1 and w1 for the first linear layer. So let's just focus on the second linear layer first. So dl, dy, db2 lets me get gradients to update b2. And then dl, dy, dc, dw2 gives me my gradients to update my w2 layer, right? My w2 weights. Okay, good, no problem. How do I get back here? How do I get back to here? Well, just look at the path. If we do dl, dy, dc, and then dc, dh, and h is the output of the first linear layer, right? H is my output of the first linear layer, and then dh, db1, well, there we go. That gives me derivatives for b1. And then again, if we do all of that times dh, da, dw1, well, that gives me everything I need for this one right here. And so there's essentially for every operation, there's a couple of different things we care about. We want the derivative of the loss with respect to all of the parameters that define that operation. In this case, it's these weights and biases, right, for a linear layer. But we also want the derivative of the loss with respect to the input of this function. In this case, it's h, because we need dl/dh to continue back propagating back, right? If we want to keep going, we need the derivative up to h so we can keep going. And so that's basically the setup for everything in PyTorch and for everything we'll be implementing. We want the derivative with respect to the internal parameters of our function, and then the derivative with respect to the input. And we'll see all of that again in a bit. Now, of course, we don't have a two linear layers typically. We'll put some activation function between them, but nothing changes, right? We'll have, again, this path to update b2. We'll have dl, dy, dc, dc, dw2 to update w2. Again, we'll go from dc, dk. K is the output of my ReLU activation, which means if I want to get from k to h, I need to do dk, dh. What's the derivative of, and this is why my activation function needs to be differentiable, right? I need the derivative of k and with respect to h. And then once I'm here at h, same thing. I can update b, I can update w, and we are good to go. Right? So that's how we can basically do everything. And this is what we'll be defining, right? This is essentially the structure of all models, and Autograd will do this automatically for you. But if it's a linear layer, I know exactly what it should be, so I could also do it myself. And we'll see all of this kind of come together in the future. Now, for transformers, these are essentially all of the operations we need to do transformers. We have linear layers, we have softmax, we have ReLU, or GLU if you want to do that, but we'll just do ReLU today to keep it simple because GLU's derivation of the derivative is not that simple. There's embeddings. There are the embedding layer for our character embeddings. We'll have layer normalization, which will be the toughest one we'll do today. We have multi-head and feed-forward. MultiHeadAttention and feed-forward layers are just a combination. It just uses stuff that we already implemented earlier. We need to implement dropout, because of course we want to help with overfitting, and then we need a loss function. And most transformers for language modeling are using cross entropy loss, so we're going to have to implement that as well. And we'll be implementing, especially for softmax and cross entropy, we'll be looking at a slower version of them and then the faster version of them. So we're going to kind of derive and implement and just kind of toggle between the two. Of course, we also need some optimizers, so we'll implement SGD is the easy one, and then Atom is also pretty straightforward, so we can implement that as well. Okay, good. So let's just go ahead and get started. Normally, I like to write all the math out, but there's actually a lot of math, so I don't think my handwriting would survive. So we're going to be, I already wrote everything out, and we're going to step through the math line by line. Let's go ahead and see if there's anything I want to do first. All right. So yeah, let's just set some boilerplate code down first, and then after that we will come back and we'll start implementing every layer one at a time. So we're going to need import Cupy SCP. Cupy by default will do all of our GPU operations, and then we'll need Numpy as NP, and then just math. Right? There we go. So we're going to have a class called operation, and an operation needs to have two things: self x, and we'll do arrays not implemented error, and then def forward self grad arrays not implemented error. So what's going on here is every single operation takes some input, at least one input, but in this case it's fine, right? So we'll have some input, and then this should be backward, sorry. And every single operation will be able to also do the backward pass, the derivative of it. And the derivative has some upstream gradient. So going back to right here, right? Whenever we're doing the derivative of this stuff right here, this dCdh is the upstream gradient to all of these operations here. So like an operation is a linear layer, and the upstream gradient is the gradient that comes into the linear layer from here. So dCdh would be that. And so we just need to make sure we define all of this stuff here. We will have a class grad tensor def init self params. It'll be self.params is params. So these will be the actual parameters in our in this specific tensor. We'll have self.shape is params.shape, just so we have an easy access to the shape. And then self.grad is none, because by default, right, at the initially, all these parameters have no gradient. And then we're going to just throw in a zero grad method here, because of course we need to, every optimization step, we want to just go ahead and zero out the grads. We'll just set the grads to none every time we want to zero them out. And then we're going to have class grad layer, right? So these will be essentially our layers. A layer is going to be a, basically it'll inherit the operation. A layer will have the forward and backward. And a layer, what makes it different is it has def parameters, right? Parameters self. There we go. So params is going to be an empty list, and we'll do for attr name, attr values in self.dict.values, right? Dot values. We can loop through, or actually not values, dot items. We're going to grab both of them. We're going to have if is instance. If the attr value, right, if the thing, if the is a grad tensor, it's a grad tensor, then we can do params.append attr values. Else, if is instance, attr values, grad layer, then we'll do params.extend attr values.parameters. And then we can return params. So if this doesn't make sense to you, we can do a quick just test here. So we can do dummy class, and we can do def init self, and we'll do self.name is pream, and self.school is UIUC, right? That's the school I go to. Okay, so if we do class is, or let's do CLS is dummy class, and we print out cls.dict. If you've never seen this before, no worries. Let's just python nn.py. You'll see that the dict dunder method essentially just gives you a dictionary of the, I called it self.name, so it's name, and the thing inside it is pream, and then self.school, it's UIC. And in this case, I've assigned these keys are assigned to a string, but these can be anything, right? Any kind of object, because it's just a dictionary, right? Internally, it's just a dictionary. And so what we're doing is a grad layer. A layer can have two things. It can either have more layers inside it, or it can have a tensor inside it. And the tensor is like the parameters of PyTorch, like in nn.parameter. And then layers are like there's more stuff inside it. So if we have a linear layer will have a weight tensor and a bias tensor in it. But MultiHeadAttention will have more linear layers inside it, and then each of those linear layers inside it will have tensors, right? So this is just me recursively just finding all the parameters of a grad layer and storing them, right? So nothing too crazy. Okay, so that is all of the boilerplate code we're going to need for now, and then we will come back to it later. So let's go ahead and start with the linear layer, right? So this is, again, I wrote everything out, so hopefully this is clear. I plan on making a nice latex version of this later, but for now this is fine. So linear layers, right? This is just y equals x w plus b, right? And for now, let's just look at it for one sample, right? So normally we train on a batch of data, but in this case, let's just pretend we're training on one. So this is a 1×3 vector times our weights, which will be a 3×1 vector, plus one bias value. No problem there. And our goal, right, is going to be compute dl dw, which we know is going to be equal to dl dy dy dw, right? Because we have to go through the loss. The loss goes to y, and then y goes to those w's. And a key idea that we need to keep in mind when we do derivatives of tensors or like arrays, right? Derivatives of, in this case, it's not really a matrix, it's just one value, but or just one column. But the derivative has to be the same shape as our original array. So that means dl dy dy dw. If w is a 3×1 array, then dy dw must also be a 3×1 array that looks like this, right? It'll be dy dw1, dy dw2, dy dw3. So that's what we see right here. Right? Nothing too crazy. And that's just a standard rule, right? It just has to look the same. And so the way we can set this up now is kind of like this. So we have essentially dl dw is dl dy, dy dw, and dl dy is just a constant, right? Because y is just a single number output, so it's just a it's a 1×1 tensor, and then our dy dw has to be this array, right? This vector in this case, dy dw1, w2, w3. Okay, well, how can we actually do this? What is dy dw1? Well, here's y and here's w1. So dy dw1, dy dw1, well, that's just equal to x1, right? This is the same as saying if y equals ax, dy dx is equal to a. So dy dw1 is x1, dy dw2 is x2, ... And so we'll just apply that right here, right? That's exactly it. dy dw1 is x1, dy dw2 is x2, dy dw3 is x3. And notice what happened here. X over here, our input was a row vector, 1×3. But x is now a column vector, 3×1. So the derivative of dl dw is just x transpose dl dy. And that's the key idea, right? Let's just keep this in mind. This will come back again in just a bit. So let's just keep going. X transpose dl dy. How do we do dl dbias? Well, that's easy. If y is equal to wx plus b, well, dl db is just equal to dl dy dy db. And what's the derivative of y with respect to b? That's just 1, right? So this term here is just 1, and we're just left with dl dy. Easy enough, right? Nothing crazy. And then dl dx, well, exactly for the same reason as before, right? If we do dl dx, that's going to be basically dl dx1, let's do the first one, is equal to dl dy dy dx1. And the derivative of y with respect to x1 is just w1, right? That's the thing we're multiplying by. And so this is just going to be dl dy times w1. And so just for the same reason as before, we're going to have a dl dy is a 1×1, right? It's just a single number. And then dy dx, x in this case, is a row vector. So that means dl dx must also be a row vector. And so this will be a 1×3. And in that case, basically we'll get something like this. It'll be dy dx1 dy dx2, dy dx3. And we know what these are. dy dx1 is w1, dy dx2 is w2, dy dx3 is w3. And w's here are now a row vector. That's a 1 by 3 vector. But what was w to begin with? It was a column vector, right? 3 by 1, which means it's simply just dl dy w transpose, right? So there we go. So these are basically the three formulas for our derivatives. If we want dl dw, it's x transpose dl dy. dl dy is our upstream gradient, right? It's what's coming in from after it. And then here, if we want dl dv, it's just dl dy because the derivative is just 1. So it's just the upstream gradient. And then dl dx is going to be dl dy w transpose. And that's it, right? That is our derivative. Now it becomes just a little bit more complicated because we don't typically train on one sample at a time. We have a batch of samples at a time. So let's just make before we had a 1 by 3. So it's one sample, and that sample had 3 features. Now we're going to do 2 by 3. We have 2 samples, each with 3 features. And that means a couple things. First, we still have the same weight matrix, right? Still the same weight matrix here, W1, W2, W3. But we now have 2 outputs, right? We're going to have an output for the first Y and an output for the second Y, right? Nothing crazy. So because we have a batch size of 2, so we should have 2 outputs, right, for each sample. And then we add a B here, but this is where it becomes a little bit complicated. We do add a B, but it's the same B to both of them. So technically, we're adding this to it, right? Like a B and a B, but both of these B's are the same because we have Y1 is equal to X11 W1 X12 plus X12 W2 plus X13 W3 plus B. And then Y2 is going to be X21 W1 plus X22 W2 plus X23 W3 plus B. And these 2 B's are the same B. So this is why it's basically broadcasting. We're adding the same bias everywhere. We'll see how we handle that in just a second. So let's go ahead and take those derivatives again. dl dw doesn't change. It's still a column vector, right? dl, just like this. And so, well, let's go ahead and see what these column vectors look like. And this is where it becomes a little bit complicated. So we want dl dw1. And the question is basically this. Our loss, so we produce a y1 and a y2, right? This our function. This goes to some loss function. And so when we backpropagate through both, and let's pick a different color for this. We're going to go through both y1 and y2. But w1 multiplied to both chains. So if we have right here, we can see w1 was used to compute for y1, and w1 was used to compute for y2. So there's 2 different contributions, and we'd have like a loss right here that's backpropagating back. And so we have a contribution to w from this upper batch, right, the first sample in the batch, and then we have a contribution to this w from the second batch, right? Basically, we have multiple contributions to the same thing. And the way that we typically do this is when we have multiple contributions, we just add all those contributions together, right? Gradient contributions together. And so, for example, let's kind of look at it here. We know that dw1, right? dl dw1, let's go back to pink, is dl dy dy dw1. But the question is which y? Because we have not just a single y, we have a y1 and a y2. This is the output of the first sample. This is the output of the second sample in the batch. And so it looks like this. We took w1 and it multiplied to x11, did some other stuff, and then produced y1. And then we took w1, multiplied it to x21, did some other stuff, and then it produced y2. And so during backpropagation, we'll get a contribution from the top chain, a contribution from the bottom chain, and we just sum those 2 contributions together. And that's the way we typically do it. We add them together because in the end, we averaged at the loss, right? The loss is a single number at the end. So in the end, this would have gone to, let's say we did mean squared error loss. It would have just been 1 over 2 because there's 2 different things here. It would have been y I minus, let's say, I don't know, let's say k was the actual answer. squared, right? And we would have added a sum here. So it'd be sum 1/2, right? Just like that. So because it's mean squared error, right? We're doing the mean squared error. So either way, so because we multiplied by half here, we can just add everything together because that'll essentially scale everything down by half when we multiply by the half anyway, when we do mean squared error. So in that case, we just sum our contributions together, which means we can rewrite this like this. We just sum up dl dyi dyi dw1, right? So from every single path, dy1 dw1 is x11, because again, if we go up here, let's erase all of you. Oh. Get rid of you, get rid of you. Okay, so dy1, let's pick a different color. dy1 with respect to w1 is x11, and dy2 with respect to w1 is x21. And we just add those two contributing gradients together. And so it'll look like this, right? We'll have dl dy1 times x11 plus dl dy2 times x21. Those are my two contributing gradients. And then we just repeat this for all of them, right? So dl dy1 x12 plus dl dy2 x22. dl dy1 x13, dl dy x23. And this is basically, again, this is my dl dw1, dl dw2, and then dl dw3. And each of these w's contributed to all of the chains, so we just add those contributions up. Here's the contribution from the first sample, here's the contribution from the second sample, and that's for all of them. And that's basically it, right? Nothing crazy. Well, can't we just rewrite this as, if we just decompose it, this is actually just writing x11, x21, x12, x22, x13, x23 matrix multiply, right, with dl dy1, dl dy2. Well, yeah, of course we can write that. It's just matrix multiplication. But what does this look like? Remember, our original data was it was 2 by 3, right? 2 rows by 3 columns. Now we have 3 by 2. We have 3 rows and 2 columns. So that is, again, X transpose, right? X transpose. So this is our final form. So the X transpose, dl dy, self-contains all of those sums over the batch. So we're good to go, right? That's it. It's as simple as that. When we do dl db, it's almost the same thing, except for one kind of convenience. When we do dl db, we know that dl db is dl dy, dy db, but we know that dy db is always just 1. So really, this is just dl dy. That's it, the derivative, just like we saw earlier, is dl dy. But again, in the same way, which y? Because this y1 contributes something, this should be 2, this y2 contributes something, so we just sum those contributions together. So we just write it like this, just sum up the derivatives by all of their contributions. So we just do I from 1 to n, however many samples are in the batch, dl dyi, and that's it. Simple as that. And in the exact same way as before, right, if we looked at the earlier one, we'll again end up with dl dy w transpose, right? dl dy dw transpose. And again, the contributions from the different samples in the batch, the gradient contribution, is all contained within this matrix multiplication, right? Because it's basically just a dot product, right? That's all that's happening. So these are the 3 key formulas for a linear layer, and they never change. It's as simple as that. We have essentially the derivative of our loss with respect to w. So let's just write them all down. dl dw will be equal to x transpose. Make sure I get it right. Oh, where did it go? Here we go. All right, yeah. So yeah, it'll be x transpose dl dy. dl db is just going to be the sum I equals 1 to n dl dyi. The reason we have to do the sum here, actually do the sum here, is because there's not like a matrix multiplication. Here, the sum is happening, it's just happening inside the dot products, right? In the dot products of those different, matrix multiplications of our rows and columns, of our x and dl dy. And then similarly, our dl dx is going to be dl dy w transpose. And these 3 formulas are all we need to implement a linear layer. So let's go ahead and implement it. So that's what we're going to do. So we're going to look at the math, derive them. I definitely recommend writing this math out once for yourself, proving to yourself that the shapes do indeed work out. That's just a good exercise. But let's just go ahead and implement it. So class linear. A linear will be a grad layer. It'll be a grad layer with a couple things. So def init, and every linear layer will have some in features, some out features, and bias equals, let's just say true. And so self.inFeatures is in features, self.outFeatures is out features. And our weights is going to be self.weight is going to be a grad tensor. And we're going to do cp.random.normal. We'll do the standard weight initialization for transformers. So scale is 0.02. And it'll be size is equal to in features by out features, right? Because in a linear layer, what we do is, and let's make it super clear, y equals x at w plus b. And so that means we're going to have x is going to be the shape of batch size, or basically, let's just say b by input, and x is, or w is going to have the shape of input by output. And our bias is going to add some value to each one of the outputs. So it's just going to be of shape output. Now it'd be easier for this to be 1 by output, so it'll broadcast when we add. So we'll just make it 1 by output for just simplicity. So there's our weight. And one key thing is, I don't know why, but Cupy has everything, and maybe Numpy does this too. Everything's like a default of float 64, which we don't want to train in because it's too slow. So we'll cast everything to float 32 ahead of time, so we're good to go. All right, so that's our weight. Self.bias is going to be, or let's do if bias, then self.bias is equal to a grad tensor, cp.zeros. It'll be 1, like I mentioned. We'll just add a dummy dimension by out features. And again, d-type is going to be cp.float32. Else bias is just none, right? We'll just set it as that. Self.bias is none. Good. So like I mentioned, every method we write needs to have some forward method, and it needs to have some backward method, right, where we define both of them. And we'll call this grad output, right? This is basically the downstream gradients from this specific layer. And so to do this, we need to let's just look at this one more time. To compute our backpropagation, we have dl dy is our grad output, right? So this thing is covered. But what we need is to store x. We have to keep a copy of x accessible to us so we can actually do backpropagation. We already have a copy of w, right? W is a part of our layer, so we can easily access it. It's just self.weight. But we need to store a copy of x temporarily for that backpropagation. So the first thing we're going to do is store that copy. Self.x is x. And our output is going to be cp.matmul, right? We're doing the matrix multiplication between x and self.weight.params, right? So we're going to access the parameters, right? Because again, the grad tensor just wraps this thing. So we're going to do cp.matmul x and self.weight.params. And this is going to go ahead and do our input by output, or batch by input times input by output, and we are good to go. And we're going to do if self.bias is not none, then we can do out plus equals self.bias.params. Just go ahead and add that on and return out. And that is basically a standard linear layer, nothing very fancy. Now it's time to do the backward pass, right? So let's go ahead and do that. So our backward self.weight ght.grad, and actually something that'll be good to mention, just for clarity, the shape of our grad output is the same shape. It should be the same shape, and this should be out. Not bad. There you go. The shape of our grad output has to be the same shape as the actual output. So the output of a layer, of a linear layer, will be, so if we do output, y is our output, it's going to be the shape of batch by output, right? Batch by output. So that means this grad output has that shape of batch by output. So we'll kind of track that as we go. self.weight.grad. Okay, let's see what that is. Let's go back right here. DLDW is X transpose DL dy. Okay, no worries, we can try that. So that's going to be cp.mapmul between our self.x transpose. That's why we have the self.x stored, so we can do that, and then grad output. And why does that work out? Because self.x is batch by our input is batch by input, batch by I, transpose, and we're mapmulling that with a batch by O. And that totally works out because we have batch by I, batch by O. When we take the transpose of this, it'll actually be I by O. Get rid of that. Right, just flip to, or I by B, my bad, I by B. And this will give us a final output of I by O. And what were the shapes of our weight? Our weight matrix is a matrix of input by output. Well, there you go. There's our matrix of input by output, because the gradients, the shape of the gradients, have to match the shape of the tensor that we actually want to update, right? And similarly, if self.bias is not none, so if we actually have a bias to update, then we're going to do self.bias.grad is equal to cp.sum grad output axis equals 0, keep dims equals true. So what's going on here? Remember that our bias tensor is a 1 by output, right? We defined it right here, 1 by output, but our gradients, or upstream gradients, are batch by output. So what we're doing is summing over the batch dimension, because every single sample in the batch has its own contribution, right? Its own contribution to the gradient. So we're going to go ahead and just sum all of those contributions up. So we're essentially just summing along this dimension. And so we can do dot sum axis equals 0, and this will give us a output. And the reason we're just doing the keep dims is true is so that extra dimension doesn't disappear. It'll output a 1 by output, the same shape as our bias. And so we're good to go there. And then lastly, we'll have self dot, actually we don't need to store that. We can just do return. This will be the thing that pops out of the model. So let's kind of go here just to check. Let's just look at this. So let's say we're doing this layer here. We computed DLDB, it was that sum. We did DLDW, but now we need to give the gradient with respect to the input to this layer, right? The input to this layer is H. We need to give the gradient with respect to this, because this is going to be the upstream gradient for future operations, right? So all we need to do is just set it up that way. So we just need to return DLDH, right? Or the derivative with respect to the input. So DLDX in this case, right? DLDX. And we, again, know the formula for that. DLDX is just the upstream gradient mapmul with W transpose. So let's just do that. Return cp.mapmul grad output, and then self.weight.params.transpose. And it's that. That's it. That's basically all we need for a linear layer. Even our more complex implementation later on is not really any significantly different from this. So there we go. That is our linear layer. What was the next operation we wanted to do? Softmax. Okay, so softmax is a little bit more challenging. So let's go ahead and explore it. All right, so we're going to do two versions of softmax. The first one's going to be a slow one. Second one's going to be better, and the one that's actually used in PyTorch. So let's just build up to it. So softmax is a vector function. A vector function is something, it's an operation that occurs across the entire vector. So for example, we have some outputs here, right? Let's say some outputs of a neural network, and we have n of them, right? So we have n different outputs here. And we have these softmax values, right? We have these softmax values. And S1, or any of the S's, Si is e to the power oi divided by the sum over e to the power ok for all k's in this vector. And this is why it's a vector function, because you can see, for example, S3 is e to the power O3 divided by e to the power O1 plus e to the power O2 plus e to the power O3, dot, dot, dot. So you can see that one value in the output of softmax has dependencies on all the different input values, right? All the values on the vector. And this is what makes it a vector function, right? Interdependency. So let's go ahead and see. There's basically two cases that this causes. And so let's just do the derivative and see what happens. We're going to first do it for when I equals j. So this is going to be, so let's kind of set it up actually. What we want is the derivative of OI with respect to the derivative of S. Actually, let me write it the other way. My bad. It should be the derivative of some SI with respect to the derivative of OJ. And the reason we can write this is because we know that SI, some S output, has dependency on all different OJs. But what we're going to see is there's a difference. If I is equal to j, so we're looking at S3 and O3, the result is slightly different from then when we're looking at S3 and anything else that isn't O3. So if we're looking at this. So we're going to write both results out. The derivative of S3 or SI with respect to OI, and then derivative of SI with respect to O not I, right? Something else. And so let's do the equals I case first. So the derivative is pretty straightforward, right? We have something divided by something, so we can just use our standard quotient rule, right? So we're going to do derivative of the derivative of the denominator, or denominator derivative of the numerator. So that's going to be the entire denominator, so sum e to the OK. Derivative of numerator. So this is the derivative of e to the OI with respect to OJ. Right? E to the OI with respect to OJ. But I know that OI and OJ are basically I and J are the same thing. So the notation is a little bit weird here, but I and J are the same. So if I do d e to the power OI with respect to d OJ, this is just equal to e to the OI because I and J are the same. If I and J were not the same, then e to the OI is technically a constant because we're not even looking at the same OI. This would have been 0. And we'll see that show up a little bit later. So because we're looking at the same I and J, derivative of e to the OI with respect to OJ is just e to the OI. Nothing changes. So there you go. So that's denominator, derivative of the numerator, minus numerator, e to the OI, derivative of the denominator. Okay, what's the derivative of this? We have e to the power O1 plus e to the power O2 plus dot 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 e to the power O n. Let's say n, big N. And I want to take the derivative, let's say with respect to O2, let's just say, of this. Well, what's the derivative of a sum? Well, that's the sum of the derivatives, right? Derivatives is a linear property, so there you go. And what's the derivative of e to the O1 with respect to O2? Well, it's not even the same variable. So as far as O2 is concerned, O1 is just a constant. That would be 0. What's the derivative of e to the power O2 with respect to O2? Well, O2 and O2 are the same variable, so this is just e to the power O2. What's the derivative of ON, e to the ON, with respect to O2? Well, ON is a different variable from O2, so this is again just 0. So you can see that essentially when we take the derivative of the vector, we kill all of the different derivatives except for the one that we actually index for, right? So this one. So we'll just end up with derivative of e to the OK with respect to OJ is just going to be OJ. And again, this I and this J here are the same. I is equal to J. I just wrote them separately just so it's clear of what's going on. Or I don't know. Yeah, that should be fine. And then we divide by the square of the denominator, right? That's your standard quotient rule. Denominator, derivative of the numerator, minus numerator, derivative of denominator, divided by the denominator squared. And now that we have that, we can do a little bit of simplification. We see we have an OI term and OI term right here. We can pull that out, and we'll just end up with the stuff on the inside, right? So it'll be the sum e to the OK minus e to the OJ. And again, this j and this I are the same thing, right? They're equal to each other. That's our assumption. And the denominator stays. And because the denominator stays, we can go ahead and split it up, right? We can just rewrite this denominator as a sum e to the OK times sum e to the OK, and give one of the sums to one of the terms, and then the other sum to the other pair of terms, right? And we can write it like this. We just go ahead and split them up. Well, what does this look like? This is just softmax. This is the softmax of e to the OI divided by the sum of all k. That's just softmax, SI. And what is the derivative here? We have e to the OK minus e to the OJ over e to the OK. Well, isn't that just if we put a big bracket around this, right, isn't this just these two things are the same? E to the OK divided by E to the OK is just 1 minus E to the OJ divided by that sum, E to the OK. Well, this is also just softmax, right? That's just the softmax function. And so that's why we get Si times 1 minus Sj. And again, remember, in this case, this I and this j are the same values. And we'll kind of write it cleanly in a bit. Now, if I is not equal to j, we saw that this term here, when we did the derivative of e to the oi with respect to oj, if this I and this j don't match, then this thing is just 0. The derivative of this with respect to this is just 0. So that's why you'll end up with exactly the same setup, but we get a 0 term here. And so basically all of this drops out. You're just left with this. You'll have a negative e to the oi divided by this, e to the oj over this. And we get, again, both of these things are just softmaxes. So we'll get minus si sj. And so notice the parallel here. When we have, and let's just write it out, when I is equal to j, we're going to have si times 1 minus sj. And because I and j are the same, we can just write si times 1 minus si, or we can write si minus si squared, right? So that's fine. Yeah, that's not a big deal. We can write it that way. That's exactly what it is, but we'll just keep it this way for now. And then when I is not equal to j, then we just have minus si sj. And actually, let's just write it out. Si minus si sj. And again, both of these are i's, so we can just write minus si si, just like that. And so that's basically the setup, right? We have all of this. And we have the derivative when I is equal to j and the derivative when I is not equal to j. And now this lets us set up the Jacobian. So if you've never heard of a Jacobian before, it's very, very simple. It's basically a matrix of derivatives. We have some O1, O2, O3, and we have some S1, S2, S3. O is my input vector, S is my softmaxed outputs. And we'll get some matrix here. And this one asks, what is D, what is the order? What is DS? DS1, DO1, DS1, DO2, DS1, DO3. And then similarly, what is DS2, DO1, DS2, DO2, dot, dot, dot. We'll have all of this. And what we found is that the values on the diagonal, right, these values on the diagonal where I is equal to j, right, so we're looking at S1, O1, S2, O2, S3, O3, that will have this derivative. And then for all the values that are not on the diagonal, that will have this derivative. And so we can just set up the matrix like that, right? Our Jacobian is just our pairwise derivatives of all the combinations. So we have S1 times 1 minus S1, S2 times 1 minus S2, S3 times 1 minus S3 along our diagonal. And then everything else is just what we had, right? Minus Si Sj. So this will be minus S1 S2, minus S1 S3, minus S2 S1, S, right? So on and so forth. And you can see this is obviously a diagonal matrix, right? So minus S1 S2 is the same as minus S2 S1, right? They're the same thing. So this is a diagonal matrix. Okay, good. So that's our softmax setup for now. So we're going to implement it, but we're going to revisit this again because there's a couple small things we still want to improve on. So let's do that. It's going to be class. I'm going to call this slow softmax, and you'll see why. So forward is very simple, self x. And actually, yeah, there's one thing I should have mentioned. Let me make it very clear. Numerical stability. So whenever we do softmax, right, we're doing e to the power a number. Now, what if x happens to be a big number? Let's say x is 100. What's e to the power 100? That's a huge number that will most definitely throw or break our stability of our, like we'll run out of numerical precision to do that, right? Our float 32 can't represent big enough numbers to do that. And so this is a little bit of an issue, but it's very easy to fix by just subtracting a c. So if we do e to the power x minus c divided by e to the power x minus c, well, subtracting by something is like dividing the exponential. So e to the x over e to the c divided by e to the x over e to the c. And these two things will cancel then, right? These two things will cancel. So it's common practice for the stability of softmax to do e to the x minus max over the vector. So like when we're doing a, if we have x1, x2, x3, the first thing we do is find the max along this vector. What's the biggest value? Let's say x2 was the biggest one. So we'll redo it of x1 minus x2, x2 minus x2, x3 minus x2. And then we just do the standard softmax on this instead. And this doesn't change any of the values because we can see because of exponentiation, this is just a constant that will get factored out in the end, or it just divides itself out, so it doesn't matter. But it makes it more stable because now look, what is the largest value in my vector? Well, it'd be 0, right? Because I just subtracted the largest value in the vector. So if I subtract the max, then the new max will end up just being 0. And so this is a simple stability trick we typically use for softmax. Otherwise, we'll just have all sorts of issues. So let's go ahead and implement it. So we're going to do, again, self.x is x. We're going to have to store this temporary output. Okay. And what we're going to do is let's do shifted x is equal to x minus cp dot max, right? Find the max of x. Axis is -1. Keep dims is true. Because I'm always going to, at least the way that we're doing it today, we're just going to assume that the max is along the last axis. So we'll have, however many dimensions we have, we'll be doing it along the last axis. In our case, we'll be doing it on word embeddings, right? So it'll be on, we'll have a data set, or our data will look like batch by sequence by embedding dim, or batch by sequence by sequence. This is our, transformer, and we'll have another one in there. Batch by number of heads by sequence, that's our attention mechanism. And then the output of attention, we need to take the softmax of this along the last dimension, right? So there you go. If you aren't super familiar about attention and transformers, you should probably go watch that first, because I'm already assuming you know that. I should have put that at the beginning as a caveat, but let's just keep going. So we have shifted x. All right. And so now that we've shifted it, we can go ahead and exponentiate it. So exp x is going to be cp.exp shifted x. Go ahead and exponentiate it. And then self.probs is just going to be equal to our expx divided by cp.sum exp x. Axis is -1. Keep dims is true, right? So that's it. I've just gone ahead and I've exponentiated everything and then divided by the sum of all those exponentials, again, along that last axis, because we're doing each one of those attention vectors individually. And we're good to go, right? We have everything we need right here for that. Let's write the backward pass now. To do the backward pass, we need to define this Jacobian, right? Let's just build the Jacobian now. And notice that this Jacobian I wrote here is for every pair of these vectors, right? So basically you can imagine that we are typically, so like in our case, right, we're going to have a sample by, or sequence length by sequence length attention matrix, and we want to take the softmax along this dimension. For every single one of the rows, we want to do the softmax individually. That's why it's along the last dimension. The thing is that although we can do this, just fine, the issue becomes that if we want to define the Jacobian, it's based on each one of these vectors. So we're going to have a, let's say we have vector 01, 02, 03, let's say just 3 things. When we do the softmax, we'll end up with another sequence by sequence thing, and we'll have our softmax 1, softmax 2, softmax 3, right? And in the forward pass, we just compute all this at once. In the backward pass, we need the Jacobian between S1 and O1, the Jacobian between S2 and O2, the Jacobian between S3 and O3. So we need to create this n by n, big matrix for every single one of these pairs. And this is basically why this is called slow softmax, because we won't actually do this in practice, but let's just go ahead and do it, right? Just so we can see it. So this can be def backward. Oh, I need to return self.probs. There we go. Def backward. Self, again, there's going to be some output upstream gradient, and the upstream gradient is in the exact same shape as the input, so kind of everything is ready to go already. And so let's go ahead and do our gradient. It's going to be self.zeros like self.props. We know that the gradient has to be in the same shape as our matrix, in this case s by s or whatever other dimensions we may have. So it'll be in the same shape. Let's just initialize it as zeros. And we know our batch size is going to be len self.x, right? Whatever the first dimension is. And so then what we're going to do is for I in range batch size for every single sample, and this is me basically looping through every single one of these rows here, one at a time. What we're going to do is our sample probs is going to be equal to self.probs I, right? Because again, remember, these s's are the outputs of my softmax, right? These s's are my softmax values. So what I'm going to do is grab my s's for this specific softmax, right? For this specific sample, right? Whatever row I'm currently looking at. And so I've grabbed that specific row, and then we're going to do j is equal to negative sample probs dot reshape minus 1 times sample probs dot reshape 1 negative 1. So what I've done here is I've multiplied. Okay, so first I have a vector of s1, s2, s3. That is my sample probs. And what I've done is I've created two copies of them. I have minus 1, 1, which will be a 3 by 1 vector. So that will look like this. Let's make it clear. So we'll have s1, and then we will have s2, s3. Right? That'll be my 3 by 1 vector. And I'm going to be doing a multiplication with a s1, s2, s3 vector here. And Numpy will automatically broadcast it, right? It will go ahead and do s1 times s1. So this will create a matrix like this: s1, 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 s2, s1, s3. And then similarly, we'll have the other ones right here as well. There we go. So this will be s2, s1, s2, 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 s3, and then s3, s1, s3, s2, s3, s3. And of course, we had this negative sign in the front. So we're going to just add a negative in front of all of these things. And that's basically our pairwise matrices, right? So we can see we've produced this, right? We have our minus si, sj for everything. But we know that the diagonal is slightly different, right? We can't just do that. So let's just rewrite the diagonal a little bit. What have we exactly done? We have, honestly, actually, it's easier if we just do it this way. That's fine. We're just going to set the diagonal to si times 1 minus si. It's as simple as that. So we're just going to do that real quick. We're going to do j cp.diag indices, right? It's just a simple method built into Numpy and Cupy that will just give you a list of diagonal indexes. So it'll be 1, 0, 0, 1, 1, 2, 2, things like that. Dot shape, we have to give it the, the shape of the matrix we want to produce. Dot shape 0 is equal to sample probs times 1 minus sample probs, right? Because that's what we have, right? This derivative here is si times 1 minus si. So there you go. That's the derivative. And this will go ahead and just update all of these diagonal values as s1 times 1 minus s1. And then the next one will be s2 times 1 minus s2, s3 times s2 times 1 minus s2, s3 times 1 minus s3. And that will go ahead and actually produce that Jacobian matrix. And now that we have the Jacobian, all we need to do is do A, let's just call it A, is going to be our output grad I at j, right? So we're going to grab for this specific thing, for this specific vector, let's say the first one, we have some gradient. We have some gradient for this whole matrix. We're going to grab the gradient for just the vector that we're currently working on and then just mapmol it, right? Because the Jacobian tells me the contributions, how these gradient contributions should be distributed to this one, right? That's the entire purpose of this matrix. How should the gradients from O1 be distributed to S1, O2 be distributed to S2, O3 be distributed to S3, so on and so forth. And so let's go ahead and do the mapmol, which will distribute how these gradients should be propagated back into our original inputs to the softmax. And so that's basically what this line is doing. And then gradient I is equal to A, right? We're going to go ahead and store for that specific row right here. And so I wrote it like this, but technically this doesn't need to be S. This can be just any batch dimension, right? Any dimension. So we're going to do batch. And just to make it very clear of what's going on, we have essentially, as a recap, we have some O1 vector, O2 vector, O3 vector. It goes through a softmax, which then produces a softmax1 vector, softmax2 vector, softmax3 vector. And then this goes on to do stuff, which means in the backward pass, it's going to get some gradients, right? It's going to get some gradients. And we're going to have gradients for, in the same shape as this. And what the Jacobians say is, how should I distribute the gradients along this vector here to this vector here through the softmax operation? How should I distribute the gradients from this vector here to this vector here? How should I distribute the gradients from this vector here to this vector here? And the Jacobian essentially sets up those contributions, right? How the input vector is related to the output vector. And there we go. That's basically the main idea. So we have now implemented softmax. Now this, and let's go ahead and return gradient. Notice that there's no, unlike we had earlier, right? Earlier we had these grads, right? We had to store these gradients, and that's because this operation, the linear layer, had some learnable parameters. Softmax has no learnable parameters, so all we need to do is take these gradients, do the transformation for whatever the backward pass is, and then just return it. And that's us backpropagating through this entire operation. Now, this is not how we actually do it in practice, because anytime you see a for loop, you should raise an eyebrow saying well, okay, we could probably do this better. Because if my batch size is very large, which it is for most interesting problems, then you'd have to for loop through each one of them, and this is just a pain, right? This is very slow. So to make it faster, we have to just rethink a little bit of what we're doing. So like I mentioned, one of our O's contribute to multiple S's, right? Because we have that sum over Si in the denominator. Well, because O contributes to multiple S's, all the S's will backpropagate back to that same O, right? We'll have contributions of the gradient coming back to this specific O. So we could technically write it like this. Our derivative of the loss, right? This is going to go on to do some other stuff, and it's going to go to a loss, right? So the derivative of the loss with respect to just one of these values, say let's say dl do2, is going to be dl dsi times dsi doj. So I want the derivative with respect to some specific oj, let's say o2, but that means I have to sum up all the contributions of the derivative onto O2 from S1, from S2, S3, dot, dot, dot. So you can see we're doing a sum over I, basically over all the different S's, and then onto our OJ. But we just did this, right? DSI, DOJ is exactly what we computed, right? And let's just kind of rewrite this in a slightly smarter way. We have, when I is equal to j, we have SI times 1 minus SJ, where I and j are the same. When I does not equal to j, then we have negative SI, Sj. Well, this is just, and we can rewrite this again, this is just Si times, or minus Si, Sj, right? That's how it is. So this term and this term are the same. This is the only thing that's different between them, which means we could write it like this. We can just use our delta, right? Or basically, an identity or indicator function, right? We can use an indicator function. Si times indicator minus Sj. This is going to become Si indicator ij minus Si Sj. And this thing is only 1 if I is equal to j. So if I is equal to j, if we're on a term where I is equal to j, then it's going to be Si minus Si Sj. And when I is not equal to j, then this is going to be 0, and we're just left with minus Si Sj. So it's just a little bit of a shorthand notation to say exactly the same thing, right? Just as a one-liner. And we have here dl dsi, and we're just going to sum up again over all the different i's. And we again know that this derivative here depends on if the I we're looking at this part of the sum and this j are the same or not. And if they're the same, we get one formulation. If they're not the same, we get the other formulation. We can go ahead and take this and split it up, right? Because we have this thing times this. So let's just go ahead and just split the product up a bit. So you have dl dsj times this plus this. And basically the split was here. I have the sum over I, but I includes j, right? J is one of the things in this I. So let's just do the sum for everything that isn't j, and then just have the jth term in the sum be separate, right? And that'll make life a little bit simpler. So what I've done is I've pulled out dl dsj, the jth term in this sum, and everything else is the same. We know the delta I and j are the same here, so delta is 1. And then I have the sum over the I exactly in the same way, but this is for all I where I is not equal to j, right? I just split the sum up. That's it. Because again, we have, essentially we'll have 1, 2, 3, j plus 1, n. So I just said I have the sum over all of this. So let's just do the sum on everything but j and just put the j outside, right? Just put j outside the sum. Just for notation, makes it a little bit easier for us to see what's happening now. So there we go. We now have our I not equal to j sum here. But this can be rewritten. We can rewrite all of this a little bit. So we have dl dsj times sj, right? That's these two terms right here. And then dl dsj times 1 minus sj times sj, right? So that's basically me multiplying this and this together with the dl dsj, and that produces that term right there, right? Nothing too crazy. And what this does is we start to see something pop up. We have this dl dsj times sj right here. We have a minus dl dsj times sj sj, and we have a minus sum over dl dsi minus si sj. Well, doesn't this look exactly like this? Yeah, of course it does. They look the same, right? So we just need to make sure we merge those terms together. So all we've done is we've now taken this sjth term and just moved it into this sum, right? We move it into this sum right here, and we're back, right? So now we have all the sums again. We have everything including j in the sum, and we just have this extra term that popped out in front. So we see here we no longer have a I not equal to j here because we just moved this term into here. This was the jth sum. This is all the sums except for the jth sum. So if we put them together, then we have all the sums, including j. So there we go. So we just, basically all we did is we took it out. We took the jth sum out. We did a little bit of simplification. We split this term up, and then the common part of that term can go back into the sum, and that's it. And so we end up with something like this, dl dsj times sj minus the sum of dl ds si sj. And now, notice what we have here. We have a sj term right here. We also have an sj right here. And notice that the sum here is over si. It's over I. So sj here, technically, is not a part of the sum. We can just pull it up in front. We can put it right here, sj. That wouldn't break anything. And so we have an sj here and an sj here. We can pull it out here, and we're left with a dl dsj, and then the sum of dl dsi times si, because the sj has been pulled out here. And now, notice what we have. What we want to do is we want to multiply every single sj value by its corresponding derivative, right, at that same index, dl dsj, minus the, if we have the sum of two different things, this is the dot product of my dl dsi and si. So this is the dot product of my si vector, my softmax, and their corresponding derivatives. And so we can rewrite this all in vector notation, where really all we're doing is s times, right, element-wise times dl ds minus the dot product of dl ds times a dot product with s. And so this is basically just a shorthand. This is doing exactly what we had done before, but notice that we've completely circumvented writing a Jacobian. We no longer, if we had, let's say, 1,000 elements in this vector here, this would have been a massive 1,000 by 1,000 element Jacobian that not only do we need to store, like compute for every single sample, but we'd have to do it for every single sample in the batch. So it'd be very, very expensive to repeat this over and over again. Doing it this way lets us avoid the entire Jacobian notation altogether. Right, so there we go. So the setup again is just rewrite this as a dot product, and we can essentially just leverage that to do it correctly. So let's go ahead and implement it. Our forward pass is identical. So we're going to do class softmax operation, And all of this is the same. And now that I think about it, we actually, this self.x, we don't even need to store it in memory, because all we used self.x for was to get the like the length, the number of samples to loop over, but whatever, it's fine. And then we're going to have def backward self output grad, just like before. But now what we're going to do is we need this dot product first, right? DL ds dot product with s. Let's go ahead and do that. This is going to be dot product. It's going to be cp.sum. We could use dot, but that's fine. Output grad times self.probs, axis equals -1, keep dims equals true. So what this is actually doing, just so we can draw the matrix out, is we have a matrix of our softmax outputs, right? So S1, S2, S3, and then we have a matrix of our gradients that are in the same shape as the output, right? Because that's always the case. So this will be DL, DS1, DL, DS2, DL, DS3, and what we want is the dot product between this vector and this vector, and then the dot product of this vector and this vector, the dot product of this vector and this vector. And so we're basically just multiplying everything together and then summing along this dimension, and that gives us our dot product. So there we go. That is our dot product, and then our gradient is going to be equal to self.probs times output grad minus dot product, right? That's the formula. We're doing our probs times our gradients minus those dot products, and that gives us everything we need for our gradient. And notice there is no for loop in here at all. And this is the way PyTorch and most frameworks will implement softmax. Good. Now that we've done softmax, what is our next operation? ReLU, right? Let's do an activation. Activations are very simple. We'll be doing ReLU, but of course you could do sigmoid or any other activation. Transformers typically use GLU, but GLU is more of a pain to derive and would be out of the scope of what we're trying to do here. So we're going to do simple and just use a ReLU activation like the original transformer paper used. And so in ReLU activations, all we need to do is basically we have an input, some input of any shape, but in this case, let's do this. And the ReLU activation says anything that's greater than 0, we just leave it alone. Anything that's less than 0 is 0. Right? That we zero it out. So if we have the vector -238, it becomes 0, 3, 8. Now, what's the derivative of the ReLU function? And this is where it becomes more interpretive, because ReLU we know is not differentiable everywhere. Of course, it's not differentiable right here, but that's okay. That's like an infinitely small area where it's not differentiable. So we can just, say an approximation. If x is greater than 0, let's just say the derivative is 1. Right? Derivative is 1, because the slope of this line is 1 when x is greater than 0. And when x is less than or equal to 0, so even for the equal to 0, just for simplicity, when x is less than or equal to 0, we're going to say the derivative is 0 because the slope of this line is 0, right? There is no slope. So there you go. That's very simple for ReLU. So we can go ahead and implement that. Class ReLU operation def forward self x, and we're going to do self.x is x, and x is equal to cp.clip, right? Very simple. Clip x a min equals 0, a max equals none. So just go ahead. We want to make sure whatever comes in for x, anything less than 0 is clipped to 0, anything greater is left alone, and we're done. So return x. Similarly, for the backward function, like we mentioned, this is going to be grad, and we call this output grad. Okay, we're going to do grad is equal to cp.zeros like self.x. Just go ahead and initialize that. And what we're going to do, so by default, we're going to basically say the gradient for everything is 0. And then for the terms that weren't zeroed out, we're going to place 1 for them, right? So that means the derivative of this term here would have been 0. But the derivative of these two terms are 1, right? Because that's what the slope of the ReLU was. So we're going to do grad self.x greater than 0, set them to 1. And then our output grad is equal to grad times output grad. Return output grad. So all we've done is take our output grad And then for the terms that actually contributed to the gradient, those get 1, and then the things that were zeroed out become 0, and we keep it going, right? It's simple as that, nothing crazy. Okay, good, so there's our ReLU function. That'll be our activation for now. Embeddings are our next layer, and this is not hard, just something to keep track of, that's all. So our embedding layer is essentially just an indexing operation, and we'll talk all about indexing in the future, but for now, an embedding matrix looks like this, right? We have the number of characters or words in our embedding matrix, and then the embedding dimension, right, for each thing. And so in this case, let's say I have 5 words in 3 dimensions per word. And so when I pass in data like this, like 0, 3, 1, 3, 2, 4, because the embedding matrix takes indexes, well, this is just indexing. This is me saying I want to get a data matrix where the first embedding is the 0 embedding, the second embedding is the 3 embedding, the third embedding is the 1 embedding. And in the next sample, my first embedding should be the 3 embedding, the second embedding should be the 2 embedding, the third embedding should be the 4 embedding. Right? So I'm just indexing. I'm just grabbing these different vectors and placing them here. And then this stuff, this ends up being, I know I didn't draw it best, but this ends up being in this case, we have 2 by 3, right? We have 2 samples, each with 3 things in them. And this becomes a 2 by 3 by 3. So we have batch size of 2, sequence length of 3, and an embedding dimension of 3. And then this stuff just goes on to the transformer and does all sorts of stuff, which means in the backward pass, we're going to get gradients that come to here. And we're going to get gradients in exactly the shape, right? Exactly the shape. And what we want to do is this, and let's just make it very clear. Basically, we're going to have gradients. We're going to have some gradient. I'm going to call this gradient 0, 0, gradient 0, 1, gradient 0, 2, gradient 1, 0, gradient 1, 1, gradient 1, 2. And so because this is just a copy operation, right? I basically moved embeddings from here to here. That means this gradient 0, 0 is going to go here to update this embedding, gradient 0, 0. And then this gradient 0, 1 came from the third one, so that'll go right here, gradient 0, 1. And then this one here came from right here, so it's going to be gradient 0, 2. And then in the next sample, we have this one right here, gradient 1, 0. Well, we already had a gradient 0, 1 in here, and we know we just accumulate those gradients up, right? We sum up all those contributions, so there you go. We've summed up that contribution. Basically, because 3 occurred twice, there's 2 different gradient streams going back, and so we're going to sum those streams up together. And then, of course, we have 2 here, so that's going to be gradient 1, 1. And then we have 4, that's going to be gradient 1, 2. And so these will be the derivatives. So all we do is take the gradients here and copy them into here. And if we have multiple uses of the same embedding, we add those gradients up together. And that's it. That's the entirety of the embedding matrix's training setup. So let's go ahead and implement it. It's very simple. So we're going to do class embedding. This is a grad layer, definite self, and every layer takes a vocab size, and an embed dim, right? Standard setup. The self.vocab size is vocab size. Self.embed dim is embed dim. And our self.weight is going to be equal to a grad tensor. So this is a learnable tensor. cp.random. And we'll use the standard again. Standard initialization. So we'll do scale is 0.02. Size is going to be vocab size by embed dim. And our dtype, right, is going to be cp.float32. We want to make sure everything is float32 precision. Okay, good. So there is our weight. And so forward is very simple. Def forward self x. We're going to do self.x is x. We're going to store these indexes. Remember, these have to be index vectors, right, or indexes. We're going to store them because I need to know where the gradient goes back to later on. So we're going to store them right now. And then we're going to do return self.weight.params x. And there we go. That's just me indexing my data. Nothing too crazy. Now, to do the backward pass, we have to use a special method called add@. And so to do that, I just want to give a quick demo of that method before we actually use it. Let's say x is, and let's just copy a example in. Right, so I have this example. I'm going to say vocab size is 4. And embed dim is 3, right? Put them on different lines. There you go. Okay. So we know that our weight, our gradients, right, for the weight is going to be the same shape as our embedding matrix, right? So the gradients for our weights, right, has to be the same shape. If we have 4 by 3, then our thing here has to be 4 by 3, whatever it may be. And let's say these were my output grads, right, that came in from my thing. So what we're going to do is cp.add at weight grad x output grad. And let's just print weight grad, and this is going to make it very clear of what's going on. Python and then dot. Which one did I miss? Oh, these should be all CP, my bad. Doing it in Cupy, gotta keep it the same. Okay, there we go. Okay, so what you see is the gradient for the first thing is all 1s. The gradient for the second thing is all 2s, then all 3s, then all 4s. That's what we have. And what I'm saying is the first thing, this first vector here, came from index 0. The second thing came from index 2. The third thing came from index 0. And the fourth thing came from index 3. So when I backward pass, we should see 2 things happen. 1, because this vector and this vector both came from 0, we should be adding these contributions up. So we should add the 1s and the 3s up, and we should expect a gradient, or an accumulation of 4 at this 0 index. And then notice that there's no 1 in here, so we never use the first tensor, so that should never get any gradients. And then we have 2 and 3. So let's just kind of see it here. We can see we have 4s here because we added up both the 1s and the 3s. So that's why we have a total accumulation of 4 here. Index 1, right, or basically word 1, vocab 1, was never used. So it gets no gradients at all. It was just an unused tensor in this specific pass. And then index 2 had gradients of 2, so there we go. And index 3 had gradients of 4, so there we go. So we can see we have an accumulation for repeated use. We have 0 when it's never used, and then it's just copied in if it's only used once. And it's just simple as that. So that's basically how we do the backward pass for this. So we're going to do def backward self output grad. And we're going to do self.weight.grad is going to be cp.zeros like, initialize everything as 0. Self.weight.params. So everything is 0 to begin with. And then we're going to do cp.add at self.weight.grad self.x output grad. Right? We're going to go ahead and say, I want you to add to here all of my I want you to add my output grads at the indexes of self.x. Right? Because remember, self.x is indexes. It just tells me how to do it. And add at basically sums things in, but if there's repetition in the indexes, it'll automatically accumulate them up. So it'll do the total sum up to that for that index rather than just one of them, right? That's why we're using add at. It's just a scatter add operation. So there we go. And once we're at the embedding layer, there is no more gradients, right? The embedding layer gets the input indexes. So at this point, we just return none. There's no gradients here. That's it. Good. What else? Okay. Yeah, let's just keep going. Up next, positional embeddings, right? So we know transformers, right? Hopefully, again, you're familiar with them. Transformers need some positional information, some kind of learnable positional embedding. Well, let's just go ahead and implement that. The positional embedding implementation is identical to our embedding implementation. So positional embeddings, grad layer, init, self, max sequence length, right? So what's the maximum context size for this model? We're not doing anything fancy like rotary or anything, just standard learnable positional embedding. Self.max sequence len is our max sequence len. Self.embedDim is our embed dim, and that's it. So self.weight, these will be our positional embeddings. Again, it'll be a grad tensor, and I can copy this from right here because again, it's the same thing, grad tensor. But this is going to have, it'll be a max sequence len by embedding them. So if I have a max sequence len of 256, I have 256 positional embeddings. Each embedding have a dimension of embedDim. And again, float 32. So to do our forward, very simple, def forward. self x, and we're going to do self.sequenceLen is going to be x.shape, like what is the length of x we're passing in, and we can throw an assertion error, like assert self.sequenceLen less than or equal to max self.max sequenceLen, right? Because if we're trying to process a sequence of 500, but my model, my positional embeddings only support up to the first 200, then that's not going to work out. So we can throw a assertion error right there. And then we can do a self.x is x, just store a copy of it, and we're going to do return x plus self.weight.params, and we're only going to add in self.sequence length worth of them, right? Because again, x is going to be, and let's kind of follow it, x is going to be in the shape of batch by sequenceLen by embedDim. So I just want to add in these parameters to these things here. Now, notice there's a little bit of an issue. My weights here are going to be in the shape. So right now it's in the shape of sequenceLen by embedDim. I make sure I clip out. If I have 200 positions, but I only need 100, then we go ahead and clip out the positions that we need. But this isn't going to work. We need to add an extra dummy 1 dimension up here in the front. That's easy enough. We can just add an extra dimension like that, right? Just so it works out. Good. So that's our positional embeddings. Def backward. Self x backward method is just as simple. Self.weight.grad is again cp.zeros like. It'll be for everything, right? Self.weight.params. There we go. And we're going to do cp.add at self.weight.grad. But what are the indexes we want to add at? Well, we want to add it at cp.arange self.sequenceLen, right? We can only contribute to the positional embeddings that were actually used. So if we have 200 positional embeddings, but we only used 100 of them, then we only want gradients added to those 100, right? Because everything else was unused. So in the same way up here, right? For tokens that are unused, they stay 0. For positions that are unused, they are 0, right? There is no contribution. And we want to add in our outputGrad.sum axis equals 0. Because remember, this should be outputGrad, I bet. Remember, our outputGrad is the same shape as our data, right? So it's going to be batch by sequenceLen by embedding dim. But remember that we added this thing here for every single sample in the batch. So this S by E matrix that we added happened to every single sample along this batch, which means every single sample in this batch contributes to that gradient. We can sum those contributions up and then place them in our embedding dimension. So basically, we go ahead and sum over them. So we'll end up with an S by E matrix at the end. And S by E is up to the sequence length that we actually processed in this specific batch. In our case, we're going to be training on the same sequence length, so it's fine. But up to the sequence length that we process, and then we accumulate those gradients into here. And again, we just do this here to make sure we sum up all the contributions of gradients across the batch. And now we can return outputGrad. Simple as that. Next, we have, and this will be the toughest one, this will be our LayerNorm. So I'm going to step through this, and there's actually one thing I forgot to add, just so we don't forget and come back to it later. For every single one of these layers, I just have this wrapper. So let me just put these here. These are just print strings, right? So I can print out the linear layer, and it tells me everything I need to know about it. So let me just paste a couple of these wrappers into them so we don't forget. That's our slow softmax. This is our softmax. We have our ReLU. There we go. We have our embedding, which will have this wrapper. Where are you? There we go. And then we have our positional embeddings. There we go. All right, nice. All right, time for LayerNorm. And LayerNorm is undoubtedly the toughest implementation out there. So before we start it, let's just recap what LayerNorm is if you are unfamiliar. So here's how PyTorch defines LayerNorm, how everyone defines LayerNorm. LayerNorm is a bunch of these vector functions. And we're going to face a lot of the same issues we had with softmax, and we'll see kind of what that is. But what we do is we take some vector, let's just think about it as a vector for now. We'll think about how LayerNorm plays out in just a second. We're going to take some vector x. We're going to subtract from it the mean. We're going to divide it by the variance of that vector. plus some, constant to make sure we don't divide by 0 by accident. And then we multiply it by a learnable scale parameter and a learnable shift parameter. So LayerNorm does have some learnable parameters inside it that we're going to have to also write the update for. Implementation is very simple. It's just the computing the derivative of this requires a little bit of effort. So we're going to step through it. And this one I definitely recommend doing yourself once, because I think it's the most challenging of all the derivatives that we are doing. But let's just kind of get to the main idea first. Our data is going to be in the shape of batch by sequence length by embedding dim, right? Standard setup. And what this means is we can actually rewrite this as batch times sequence length by embedding dim. So this is basically saying that I have, let's say I have a batch of 2 and a sequence length of 6. That means I have 12 total tokens across all the batches and all the sequence lengths. And each one of those 12 things have an embedding dim of embedding dim, whatever E is. And so what we want to do is compute the mean of along E, the mean along the standard. Basically, we want to compute the mean of E and the variance of E, and then use that to update our stuff. The problem is that you can see that our computation of this, of E, like along the E dimension, it's a vector function. It's a vector function because if we have, let's say we have E1, E2, E3, well, what is the mean? The mean is going to be E1 plus E2 plus E3 divided by 3. So this mean computation I did has contributions from different things along the vector, right? So it's again a vector function, right? And this is one of those, and let's write it down. Let's say we had a batch of 2 by 6 by 3. That means we actually had 12 by E things. So we had 12 vectors, each with a dimension of 3. And here's one of those 12 vectors. And I want to compute the mean along this vector and the variance along this vector. And when I do the mean or the variance, right, as we will see in a bit, these are vector functions, right? So there's basically, we have one value with contributions from different values along the vector, just like we did for softmax, right? Just like we did for softmax. Because in softmax, let's just go back real quick. We saw that one of our S values, softmax values, was based on a bunch of the different output values, right? So it's a vector function, just like before. So we're going to have to do the math for this. And it's a little bit long, but we're going to step through it in as much detail as we can. And I promise I will come up with a nice LaTeX version of this so you can reference it in the future. So let's just start from the top. Our data is, again, batch by sequence by embedding. And what is the mean? Well, mu is just going to be 1 over E, the embedding dimension. We're basically doing the mean of each embedding, right? So this is layer normalization. If we did batch normalization, we'd have the mean. We'd do the mean along the batch dimension, but we're not doing that. We're doing layer normalization. We'll talk about batch norm when we do implement convolutions and stuff in the future. So don't worry about that right now. So we're going to be implementing right here for this, along this embedding. So we'll basically have some embedding vector, E. Let's just pretend we have one of them for now because it doesn't matter. And what we want to do is compute the mean along this, the variance along this, and everything else. So mean, mu, for a specific batch and an index in our sequence length is just 1 over E sum of x, standard mean. And then variance is, again, standard 1 over E sum of x minus mu. So we can see this mu here is reused right here, and we square it, right? And our x hat, so if we pull this back here, I'm going to say x hat is this thing right here, and then x hat is multiplied by something, and then we add something to it. So we have x hat right here. It's just our x minus the mean divided by the square root of the variance, right? Standard. It's just basically standardizing our vector x. And our y, our final output, is going to be that x hat times our learnable scale parameter plus a learnable shift parameter, right? And our goal is, given our upstream gradient dl dy, we need to find 3 different things. We need dl d gamma. We need to learn that scale parameter, dl, d beta, we need to learn that shift parameter, and dl, dx, we need to find the derivative with respect to the input, because x goes in, it gets normalized to x hat, which then becomes y after it's multiplied by, gamma and beta. And this is with the mu and the variance. So we kind of have a couple things going on in here. And so we need to find all of these derivatives and set them up. And this requires a little bit of effort. So let's just start from the top. So remember our batch and sequence length index, they're all independent. We basically, if we have a bunch of these embedding vectors individually, right, each of these embeddings are going to be normalized on their own. There is going to be some contribution to gamma and beta across this dimension, but for now we don't have to worry about that. Let's just think about it one at a time. So instead of dealing with all these extra dimensions, let's just not do that. Let's just think about doing one vector, just to keep it simple. So we have mu, and I'm just going to define some things again. So mu is, again, same thing, just the mean. I should have used a different letter here, but I'm going to say u, not mu. U is the mean centered data. So x minus mu is a u. I'm just defining that way, just for simplicity. And then my variance is just, well, variance is x minus mu squared, right? It's 1 over e x minus mu squared. But I already said x minus mu is u, right? U. So we can go ahead and just use that, right? Use that. So there we go. So we now have our, we're just defining some things. Our denominator, if you remember, was the square root of the variance plus some epsilon, right? So we don't divide by 0. So there we go. X hat j, right? So x hat was our mean center data. So x hat was x minus mu over square root of sigma squared plus epsilon. And I called x minus mu our u parameter. And sigma squared minus epsilon, I called this s, so it's just uj over s, right? Uj over s. And I also have this j thing here because I keep, let's make this clear. We have a vector of like x1, x2, x3, xn, whatever it may be. Xj is one of these x's, right? It's one of them. So we're computing the derivative for one of the elements in our thing. And lastly, our yj is just going to be xj times its gamma plus beta. So basically, let's kind of maybe draw out the vector notation for this so it's clear. I'll just assume we have an embedding dim of 3, right, to keep it simple. So we have, let's say, input is x1, x2, x3. From this, I can compute a mu and a sigma squared, right, along these things. So then what we do is x1 minus mu over sigma squared, x2 minus mu over sigma squared, x3 minus mu over sigma squared. And these are our standardized values. So this ends up being our x hat 1, x hat 2, x hat 3, right? And now that we've done all of that, we multiply each of these by a scale and a shift parameter. Our gamma is going to be gamma 1, gamma 2, gamma 3. We'll have one gamma for each one of these things. And then our bias will be the same thing. We'll have a beta 1, beta 2, beta 3. And so this will end up being x1 hat times gamma 1 plus beta 1, x2 hat times gamma 2 plus beta 2, dot, dot, dot. Right, you get the idea. So we're going to be doing that way, just to set up a little bit more context of the additional operations that will happen, and that's this stuff here. And so gamma will also have a j index, and beta will also have a j index, because for every single x along our vector, we'll have a gamma to multiply it by, and we'll have a beta to add to it. And our upstream gradient, right, is going to be up to here, dl dy. So we have everything up to the y, and we need to backpropagate through all of the stuff that we just mentioned here, okay? And we'll be calling the gradient this, right, just delta j. Okay, so let's start from the top. dl dxi, right? So if we want the derivative of the loss with respect to the input x, right, the original input x, so let's draw that again. X, we'll have some xi becomes xi hat becomes y. Well, there's multiple ways, right? Because when we compute all our stuff, we know that our x hat is based on all of the different xi's, because mu is computed with all of the i's, all the different i's along the x, and our variance is computed with all the different i's along the x. So we need to sum all those contributions up, just like we did for softmax. So we have the sum here over all the different j's, basically every single index in our embedding dim. It'll be dl, dyj, dyj, dxi. And we're going to have to set this all up. So this is basically us summing up all those contributions. How was this specific yj related to any one of the x inputs? So if we write it out again, we'll have x1, x2, x3, and then the output will be y1, y2, y3, and we know there's interdependency. We know that y2, for example, was somehow contributed to by x1, x2, and x3. So we need to go ahead and do it exactly the other way. If y1 is contributing, let's draw it the other way just so it's clear. If we know x2, for example, contributed to everything, right, through the mean and the standard deviation along the vectors, which means during the backward pass, we need to sum those contributions up, So it'll be dl, dyj, dyj, dxi for the I that we want, summing along all the different contributions that are possible. And this is the thing we'll be expanding out now. So this is going to be equal to dl dyj times dyj dxi. Okay, so dl dyj, we already wrote this notation here, right? We're going to be using this delta. So there we go. Delta j, this is again all of our upstream grads, right? Upstream gradients. But we can actually separate this out because we know we don't go straight from x to y. We go from x to x hat and then x hat to y. So dy dxi is actually dy dx hat dx hat dxi, right? We have to go through this intermediate hat parameter just for convenience, right? So we can actually write it out. And we know that dy dx hat is just gamma j. Why do we know that? Because y is just gamma x hat plus beta. So dy dx hat must be just gamma. So there you go. It's just the gamma parameter just for each one of the j's as we go across that dimension. And so then we're left with dx hat dxi, dx hat j dxi, and this is the gradient that will be challenging to derive. So that's what we'll be spending the next part doing. So let's go ahead and solve this. So let's find the derivative. We know we have the mean, for example, mu, and we want the derivative of mu. So how can we do that? So if mu is equal to 1 over e times the sum of xk, well, what's the derivative of mu? Well, it's just 1 over e. Because, of course, when we do d mu dxi, right, just like we had before in the softmax, not all of these x's will survive. We have x1, x2, we have x1 plus x2 plus x3 plus x4, dot, dot, dot. If I want d dx2 of x1, x2 added all together, dot, 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 well, dx1, dx2 is 0 because x1 and x2 are two different parameters. dx2, dx2 is just 1 because they're the same, but dx3, dx2 is 0 again. So basically everything is 0 except for the thing we want, and so that'll be 1, and so the only thing we're left with is this 1 over e constant for that one term that we have. And so there we go. Very simple. uj, right, so u is our mean center data. It's going to be xj minus mu. So the derivative of u with respect to this is, well, it's very simple. Derivative of u du dxi, if we do du dxi of xj, well, that's equal to 1 if I equals j, and 0 if I does not equal to j, right? Because if we're doing du xi with respect to xi, then it's 1. And if it's du xj with respect to xi, if I and j are not the same, then it's 0, just for the same reason as earlier. So we can just use that delta notation, right? Just our indicator function. And the derivative with respect to mu is just 1 over e for the same reason as before, right? It's just 1 over e. Good. So that sets up our next piece, right? We have our derivative of u. Now, what about sigma squared? Well, d sigma squared dxi will be the same thing. We have 1 over e times all this stuff, we just know now that when you take the derivative, we have to chain it. So the 2 will come out in front, we subtract 1, we're going to get 2 uk times duk dxi. Okay, if it's duk dxi, then we just do that? Yeah, of course we did. That's right here, right? We just solved that. So this thing will just become like this, right? uk times delta ik minus 1 over e. And the reason we have all these indexes is I had ij earlier, right? ij, but we're looking at k in this case. Sorry, don't know why I flipped the index or changed the indexes, but that's fine. Just keep going with it. We have ik here instead. It's the same thing. And so that's our indicator function. And we can now do a little bit of simplification. We know that we can split this up, so we can do uk times delta ik minus uk times 1 over e. And we know that this is 0, right, if I is not equal to k. So let's go ahead and set that up, because if we have a sum, for example, we're doing the sum of k equals 1 to e, uk delta ik. But this is an indicator function, so this is going to be like u1 delta 1k plus u2 delta 2k plus u3 delta 3k dot dot dot. But whichever, if k, let's say k is equal to 2, that means this will be u1 delta 1 2. That's just 0 because k is not equal to 2, I is not equal to 2. This is going to be delta 2, so it'll be delta 2 2. This is going to be 1 and my u2 will survive. Again, this will be delta 3 2. 3 does not match 2, so this is going to be 0. And so for in that way, right, so we're basically, because it's an indicator function, we're just selecting the one thing in the sum that we can keep and everything else disappears. So it's just ui because it's the ith term that we want, right? When I is 0 if I is not equal to k, and it's 1 when I is equal to k. So only the ith u will survive that sum and everything else gets zeroed out. Good. And then we have the 1 over e can just pop out in front, as you can see right here, and we have the sum over uk. So let's do a little bit of simplification. What is this? uk is mean-centered data. It's x minus mu. Well, what's the average of mean-centered data? Well, it has to be 0, right? If my data is centered at 0, because I've mean-centered it, and I take the average of it, well, the average of data centered at 0 is 0 by definition of the average, right? So this thing here, if we write duk, well, that's just 1 over e times the sum of xk minus mu. This whole thing here must be 0, just by definition of mean, right? Nothing else. And so we're just left with 2 ui over e, just like here. That's our derivative with respect to our variance, right? D sigma squared dxi. So we're kind of knocking out some of these derivatives. Let's go on. We now need s. S is sigma squared plus epsilon. Well, we already did some work on the sigma squared, so we'll be able to use that. Let's take the derivative. ds dxi is going to be 1/2 pops out in front, negative 1/2 at the top, standard derivative rules right there. So we have 1/2 sigma squared plus epsilon to the power negative 1/2 times the derivative of the inner operation, chain rule. So d sigma squared plus epsilon over dxi. Now epsilon is just a constant, right? So we know this is just going to be 0. We don't care about that. So really it's just d sigma squared over dxi, and we just did that, didn't we? That's right here, 2e over ui. So that's what it is. So we have 1/2, or yeah, we can put the whole thing in the denominator. So 1 over 2 square root of sigma squared plus epsilon times 2 over e ui, because that's what we had right here. That's what we solved for. And this 2 will cancel, and we're left with ui over e and square root of sigma squared epsilon, which we defined this, right? We defined it as s. So this is just ui over se, and that's it, right? So that's the derivative of s with respect to xi. So you can see that what we're trying to do here essentially is we defined all of these operations, right? All of these kind of things here, and we found the derivative of this, we found the derivative of this, we found the derivative of this, we've just found the derivative of this, and now that we have all these pieces, we have mu and we have s, so we can now go ahead and find the derivative of the thing we care about, xj with respect to xi. x hat j with respect to xi. So we have all this. So now we can do x hat j, right? So like we said, x hat is equal to x minus mu over square root of sigma squared plus epsilon. And as shorthand, x minus mu, we wrote it as uj, and this denominator we just wrote as s. So we have x hat j is just uj over s, which we can write like this. Now we want to take the derivative of this with respect to some xi, just like we've been doing up till now. The thing is that uj is some variable, right? Uj, some variable that depends on u, which contains xi, and 1 over s, or s, is another variable that depends on xi in the variance formula. So these are two different things that have xi in them internally, which means the only way to take derivatives of them is via the product rule, right? So we'll just do the first thing times the derivative of the second thing plus the second thing times the derivative of the first thing, standard product rule. So it'll be uj times derivative of 1 over s dxi plus duj dxi 1 over s, right? Very simple. And so we have two different things, and we just have to do some math now to simplify them down. Let's start with the first one. Uj is 1 over x, derivative of 1 over s dxi. That's just going to be, by chain rule, uj times dxi s to the minus 1, right? That's basically the derivative that we're trying to do. And the derivative of s to the power negative 1 is negative s to the power negative 2. And we move inside, right? Chain rule. So now we're going to do ds dxi uj. We already did that, right? We know it is this, right? So we've already done a bunch of this work already. And so let's go ahead. We had the uj right here. That's uj. And we have our, here, let's actually refer back. So we have ds dxi, which we had right up here, right? This term that we came up with right here, ui over se. And we had that uj term right here. So all we're left with now is uj times that ds dxi was ui over se, and we have the negative 1 over s squared kind of right here. And so we're just left with negative ui uj over s squared times s, so that's s cubed e. So that's the derivative of that very first term, right? That's this term right here. The second term is uj dxi. So we want to do the derivative, basically what is this derivative right here, right? This derivative, uj xi. So it'll be xi, and we have that 1 over s in front that we can ignore for now. So this is, we saw earlier, the derivative of this was just that delta function, or the indicator function, right? Delta ij minus 1 over e. We still have that 1 over s, so we can go ahead and just multiply it all together. So what we can do then is our final dx hat dxi, right, is just going to be the first thing plus the second thing. So it's going to be all of this plus all of this. Okay, so let's just write it all down, right? Let's just write it all down. So we have ui, uj, and oh, I forgot the, should be a uj right there, right? So minus ui, uj, s cubed e plus delta ij, 1 over e times 1 over s. So, you know, we're just putting it all together, nothing fancy. We can just reorganize this a little bit. We have a 1 over s here, and we can just pull everything out with the 1 over s. So pull a 1 over s out. We'll have a 1 over s in the front. We'll have s squared here instead, so it'll be minus ui uj s squared e, just like that. And we'll have a minus 1 over e right here, and the delta ij right here. So it's delta ij minus 1 over e minus ui uj s squared e. Nothing fancy. Now that we have that, we can do some more simplification. We have ui, uj, and we have an s squared. So why not just split them up, right? We can do ui over s times uj over s times 1 over e. And what was u over s? U over s was x hat, because this u was x minus mu, and this was square root of sigma squared plus epsilon. And so we have basically x hat. These are x hats. So this is just x hat xi, and this is x hat xj. And 1 over e is just a constant, so that e just goes to the denominator. This 1 over e is just a constant, so it just stays there. And this is our indicator function. And there we go. Okay, so we're almost there, home stretch. So what we need to do now is remember that this was the setup. This is where we started, right? We want to sum up all of the different contributions This was, again, if we go back to the very top of where we began, right here, right? We wanted to sum up all of the contributions of how an output y, how all the different output y's contributed to one of the different x's. And that's why we're looking at dl dyj for a specific xi, right? Add up all those contributions. And so we summed up all those gradients. We had a formulation for this. We knew this was just gamma, so that's not a big deal. And so what we were solving for is this, dx hat j dxi. And that's what we exactly solved for right here, right? That's what we ended up with. We had our formulation for dx hat j dxi. And so we can just plug it in right here. We had this, that's our upstream gradient. We already had that, that's our gamma to get into the x hats. And so now we just multiply by that, which we have our formulation for, right? We just solve for that. And so now that we have that, let's just split it all up. So we're going to just distribute these three terms. Actually, the 1 over s can just come out in front. It's a constant. So we're going to distribute these two terms to this term, and this term. So we're just going to do, it's going to be sum. All of these sums are to e at the top. Should have been a little bit clear. It's going to be delta j, gamma j, and this identity function. Or I keep saying identity, indicator function. Sorry, indicator function. And then we have delta gamma times 1 over e. Sum of delta gamma times 1 over e. And then we have the sum of delta gamma times this stuff right here. So I'm just separating all them out, right? So I have my first sum with all of the terms, second sum, all the terms, third sum, all of these terms here. And we can do a little bit of simplification now. We know that, just like before, this only exists for the ith term, right? Only for the ith term. Every other term is zeroed out because the indicator function is 0 for when I is not equal to j. So in this sum, the only value that actually survives this sum will be the delta I gamma I. So there you go. Delta I gamma I is the only thing that survives that sum. The second term, there's nothing really we can do with it right now, so we'll just leave it alone. And then the third term, we have basically, remember the sum here is over the j index. So this xi is not really a part of that sum, so it can just come out in front. And then everything else stays inside. So that's what you see right here. And these things look a lot like averages, right? Like 1 over e times the sum of something that has e elements in it. 1 over e, or something over e, times the sum over something that has e elements in it. So these are just averages. And so let's just kind of think about it a little bit. We will do one more redefinition here real quick. We know that this one right here, delta, is dl dy, the upstream gradient. And then gamma was our dy dx hat, right? dy dx hat. So for simplicity, like if we look at our chain again, we had x went to x hat, went to y. And then in comes our, from here is our upstream gradient, and then here was our gamma, right, to get there. Sorry, let me rewrite that better. This is our, yeah, actually, no, that's correct. Yeah, this is our upstream gradient, and then this was our gamma. There we go, that is correct. And so that's why you see these two terms here all the time. You'll have a gamma, where is it? You'll have upstream gradient times gamma, upstream gradient times gamma, upstream gradient times gamma. Because what we really cared about was the derivative of x hat with respect to x, right? That's the derivative that we've been working so hard to compute. This one's easy, right? Because it's just multiplied by this gamma constant, not constant, but this gamma parameter. At the x hat is multiplied by a gamma parameter. And so what we need to do is essentially, or what we're going to do just for simplicity, is if we just want the upstream gradient up to x hat, like all the way up to x hat for this last little part here, we're just going to redefine, we're just going to call it, I think called a gamma tilde. It's going to be gamma lambda, just for shorthand. So I just say the full upstream gradient up to x hat, so kind of going through the y to the x hat, I'm going to call it gamma tilde, just for simplicity. So that makes our notation a little bit shorter. We have gamma tilde minus 1 over epsilon, gamma tilde minus xi hat over epsilon, again, gamma tilde x hat j. So nothing fancy. We just had a new notation for these terms, so we can just write it as one thing rather than two different things every single time. Nothing fancy. And these, like I mentioned, look like averages. They look exactly like averages. This is the average gradient of the, up to x hat, up to x hat. So this is the gradient up to x hat. So mean of my gradient up to x hat. Mean of my gradient times x hat up to x hat, right? And this is basically, this looks like a dot product, right? So it's just a dot product. So it's taking the average of our dot product. And then this again is just delta hat, delta hat, there's really nothing to do here. And 1 over s is actually sigma squared plus epsilon. So this is our full formula for the derivative of our output of our layer normalization with respect to the input x, right? So this is our dl dx. And that's it, right? So again, this is a little bit more challenging of a, it's just some algebra, right? It's not that hard, but I would definitely recommend just trying to do this math once on your own. And again, I promise I will have all this in a nice latex sometime soon in the future. But for now, let's just keep going because we still are missing one piece. We have computed dl dx, but that wasn't the only thing we wanted, right? We also wanted, if we remind ourselves, where did we do it? I think it was higher up. Yeah, here we go. We wanted dl dx, check. But we also need dl d gamma and dl db because these are learnable parameters, right? So if they're learnable, we need gradients. And luckily, the gradients for them are very, very, very simple. We had, let's just draw it out again. We had x goes to x hat, which then gets multiplied by gamma plus beta, and it becomes y. And we just want the learnable, we just want the gradients of this and this. So all of this stuff here doesn't matter. These gradients only depend on the upstream gradients. And so you can see, just like we did before, for the beta, we sum up all of the derivatives that contributed to it. So we just do a quick sum, and that's it. And for our gamma, well, it's going to be y was equal to the gamma x plus beta. So for gamma, we're going to sum up all of the upstream gradients times the x that it was, x hat, all of the x hats that it was multiplied by, right? Because that's the derivative. The derivative of this with respect to gamma is just x hat. So if it's just x hat, then it's going to be x hat times the dl dy, right? All the upstream gradients. So it's going to be upstream gradients times x hat. The derivative of y with respect to beta is just 1. So it's just 1 times our upstream gradient, which is just upstream gradient. And again, we add these up over our batch. Because remember, we have everything we've talked about up till now is normalization of a single vector, right? Single vector, one at a time, individually. They don't see each other when we normalize things. That's what makes it layer normalization. But when we do all this, we do need to make sure that we do have a gamma parameter, right? We have gamma weights, right? Gamma 1, gamma 2, gamma 3. Let's say we only had 3 things. Then we had a beta 1, beta 2, beta 3. We only had 3 things. But we added this gamma to everything along this dimension. And we added this beta to everything along this dimension. So every single one of these things contributed to gamma and beta. So we need to sum those contributions up. And that's why we're doing the sum over all the batch and sequence length dimension, sum over the batch and sequence length dimension. Okay, so that's it. That was the toughest one that we're going to be doing. Layer normalization is just kind of, it's not hard, just a little bit of mathematical manipulation, but we are good to go. So let's go ahead and implement it. Class layer norm. This is again a grad layer self num features, right? So how many features do we have? What's the embedding dimension essentially that we're processing? And some EPS. We're going to say 1e minus 5, I think is the standard. So there we go. Self.num features is going to be num features. And we know self.eps is going to be EPS. And self.gamma is going to be our grad tensor, CP. And the standard initialization is assume a variance of 1 and a mean of 0 for the initial gamma and beta. So we're going to do ones, self.num features, And dtype is again going to be equal to dtype cp.float32, and self.beta is equal to grad tensor cp.zeros self. Num features dtype equals cp.float32, right? And so let's do our forward method first. Forward is easy. Self x, and remember and I'll kind of copy this statement in. Right, very simple. We just have batch by sequence by embedding them. I'm just assuming that that's what LayerNorm typically processes, so that's what we're going to be doing. And we need to store, right? So we're going to do self.x is x. Go ahead and store that because we're going to need it for the backward pass. And we're going to do self.mean is going to be cp.mean x axis equals -1, keep dims equals true. So basically we're computing the mean of each one of these vectors individually, right? Just like we wanted to. And in the same way, we're going to compute the variance of each one of those vectors individually. So cp.var. And we can now go ahead and normalize it. It's going to be self.x hat is equal to, and notice I'm storing x hat again as a variable because I'm going to need it in the backward pass. X minus self.mean divided by cp.square root self.var plus EPS, right? And self.EPS actually. There we go. And then finally our output is going to be self.gamma.params times self.x hat plus self.beta.params. Return out. So that is our forward pass, right? We take data, compute the mean and variance of each of these embedding vectors individually, go ahead and subtract the mean, divide by the variance for each of those vectors individually, and then scale by our gamma and add our beta and return it. And that is our forward pass of the LayerNorm. And all the effort we really did was on that backward pass. So backward self output grad self.gamma.grad is going to be equal to, so let's just start from the bottom. We know that our gamma, the derivative for gamma and beta, for gamma is just the sum over all the dimensions, right? So in our case, it'll be x. So our data's batch by sequence by embedding dim. So it's going to be over dimension 0 and dimension 1. So the sum over these two dimensions times our x hat, right? So let's go ahead and do that. So we're going to multiply them together and then sum them up. So it's going to be, let's see here, cp.sum, and we're going to do output grad times self.x hat. That's why we stored x hat as a variable so we can access it. And axis equals 0, 1. We're going to go ahead and multiply these two things together and then basically sum them up. And this will lead to a single vector of length, whatever our embedding dim is, whatever this is, num features. Our beta grad will be identical, right? So this is going to be our beta grad, but we won't multiply by anything here. It's just going to be the sum of our output grad 0, 1, just like we had here. We'll just take our grad and sum up over these two dimensions, as these were all the contributions for the gradients, because every gamma and every beta, or our single gamma and our single beta, was applied to every single token along every single batch dimension and every single thing along the sequence dimension. So there's all these contributions. We want to add them all together. Now we need the grad with respect to the normalized inputs. So dx hat is going to be output grad times self.gamma.params. So this has to do with this step that we did here. We said that we didn't want to keep writing this over and over again. So gamma tilde is just our upstream gradient times gamma, right? So that's all we did here. Our upstream gradient, so this is our tilde, is going to be the output grad times self.gamma.params. And this will be in the shape of batch by sequence by embedding, right? So we just multiplied each one of our output grads by this thing, and Cupy or Numpy will automatically broadcast it for us. We could have also added the extra dimension here. It wouldn't make a difference. And just we need the var EPS. So we know that the right here, S is square root of sigma squared plus epsilon. So let's just create that. So it's going to be, so we don't have to keep writing it over and over again. It's going to be self.var plus self.eps. That's how we stored var as another one of our variables. So we can access it right now. And so finally, LayerNorm backward. This is going to be mean 1. So we have two different means. We have this mean here and this mean here. So let's do the first one first, right? It's going to be equal to cp.mean dx hat. Axis is -1, right? Because we're gonna, again, we want to do this, our data set up like this. We want to compute the mean for each one of these embeddings individually, so along the last dimension. And then we're going to do keep dims is true, just so we don't lose that last dimension. Mean 2 is again cp.mean. And this one's going to be dx hat, right? So our tilde times actual x hat. So we can do that. So it's going to be dx hat times self.x hat. Axis is, again, axis is -1. Keep dims is true. That's mean 2. And so dx, our final derivative, is going to be our 1 over our square root of this thing. So we're going to divide by this. It's going to be dx hat minus mean 1 minus x hat times mean 2. So it's going to be dx is equal to dx hat minus mean 1 minus self.x hat mean 2. And we're going to divide by cp.square root var eps. And we return dx, and that's it. That's our entire layer normalization implemented. So it was a little bit of work, right, to get this formulation, but hopefully it was helpful just to see how it all comes together. This is the toughest one that we were going to do. So I am glad we got it out of the way. All right. Which operation shall we do next? MultiHeadAttention. Okay, now we're close to home stretch. We have a little bit more work to do, but things like MultiHeadAttention are not hard. We don't have to do too much extra work. It's just going to leverage all the stuff that we've used already. So MultiHeadAttention has some linear layers, and it has a softmax. So we're going to have to include all of them. Class MultiHeadAttention, and it's going to be grad layer definite self embed dim and num heads. And maybe it'd be best to see the pathway first. So again, I'm already assuming you're comfortable with transformers. This is not the place to start if you need to learn about transformers. I have plenty of videos for that you can go look at. But let's just remind ourselves the forward pass of attention, and then we'll look at the backward pass after we're done. So the forward pass is we have some data x. X is in the shape of batch by sequence length by embedding dim. And x goes to 3 different projections, right? Q, K, V, because we're doing GPT, right? So this MultiHeadAttention is self. We're doing self-attention, right? Self-attention, and it'll be causal self-attention because we'll be implementing a GPT type model. But we take x and it goes to these 3 different linear layers, right? 3 different projections, and we get QKV. And then Q and K, we multiply them against each other, QK transpose, we get some values, our pre-softmax values. We divide it by some constant square root of E. And then, we get that right here. And then this thing goes to the softmax and it produces some probabilities. And then these probabilities are multiplied with V to get an O, right? We do P times V, or the matrix multiplication between P and V. We get some O is PV. And then this will go on to get some loss, which means in backpropagation, we're going to get some gradients that start right here, right? Start right here. I am missing one layer. After this output, there's one more linear layer, that final projection layer in the setup, but that's fine. We'll add that in, no problem. So let's just do a standard attention implementation first, and then we'll talk through the backward pass because it's not hard. You just have to make sure we do it in the correct order. So embed dim is embed dim. Self.num heads is num heads. Self, and we want to make sure self.headDim is equal to embed dim divided by num heads, and we're going to just throw in assert self.headDim times num heads is equal to embed dim, right? Make sure your headDim is divisible. or your embed dim is divisible by num heads, right? So we want to make sure that it's divisible. Good. So we'll have a self.QLinear. Well, we already defined a linear layer, didn't we? It's going to go from self.embedDim to self.embedDim. And self.KLinear is going to be a linear layer, again, embedDim to self.embedDim. And lastly, self.VLinear is going to be a linear layer from self.embedDim to self.embedDim. So that is our 3 linear layers for QKV. And like I mentioned, I didn't have it in the figure, but there's actually one more linear layer at the end of computing attention. That's our out linear, right? So self.outLinear is again another linear layer, self.embedDim to self.embedDim. And then we have self.softmax. Softmax is soft. We're going to need a softmax, right, to compute our things. And this is going to be easy because we already wrote these methods, right? So we're just going to leverage them. So in our forward method, we're going to pass in some x, and we're going to pass in some potential attention mask, right? For now, we're going to set it to none. Okay, so our data is going to come in as batch size by sequence len by embedDim is x dot shape. That's the data we're going to pass in. And the first thing we need to remember is the linear layer that we wrote up here. This linear layer expects our data to be in the shape of something by input size, right? In our case, we have 3 dimensions, batch by sequence by embedDim. And our input size here, I, is our embedDim. So because this linear layer only supports 2-dimensional inputs, just because we wanted to keep it as simple as possible, we could have also we could have worked harder and made sure this linear layer could accept any dimension number of inputs, but I wanted to keep it simple. Because this only supports 2-dimensional inputs, like basically a matrix, we need to make sure our data is reshaped to that. And so this is the first thing that we're going to do. We're going to do x flat is going to be equal to x dot reshape batch size times sequence len by self dot embedDim, right? So we're going to go ahead and flatten them. So my data is now a matrix of 2. We had 3 dimensions. Now we only have 2 dimensions, and we can do our linear layers. So we can do q is equal to self.qLinear.forward x flat, right? We'll go ahead and pass it through, and we're going to repeat this 3 times. We're going to q, k, and v. So it'll be our k linear and our v linear. There we go. So we've done our 3 different projections of our x flat. And we just flattened it again just because our linear layer expects 2 dimensions, just for simplicity. And now what we're going to do is our data is in the shape, right, of batch times sequence by embedDim. But that's not what we need. What we want is the number of heads. So let's go ahead and do this. We're going to do q is equal to q.reshape. We're going to go ahead and do batch size by sequence len by embedDim. So this is going to take this and let's do self.embedDim. And this will go ahead and take my batch and sequence len and just separate them out again. And we have our embedDim right here. But we don't really want just embedDim. We want embedDim to be split into self.numHeads by self.headDim, right? So now we have batch by sequence by number of heads by headDim. But remember, in transformers, we want to parallelize across the number of heads. So we really want to flip these 2 dimensions and make it batch by number of heads by sequence len by headDim. So let's go ahead and do that. Dot transpose. And we'll just provide all the dimensions, 0, 2, 1, 3. So it's going to be batch size 0, 2 num heads, 1 sequence len, 3 headDim. And that goes ahead and puts our data in the correct shape for multi-headAttention. So again, it'll be q, k, and v, right? They're all going to be the same. And of course, we're going to have to transpose the k again because it's going to be qk transpose. We'll get there in just a second. So now we're going to compute our scores. Like I mentioned, it's going to be q, and let's do cp.matmul q with k dot transpose 0, 1, 3, 2. So I could have probably just put it in the correct shape up here and not done this, but that's fine. So we wanted 0, 1, 3, 2. So that will make it, essentially we're just flipping these 2 dimensions, right? So it can be so our q is num heads by headDim, And our k is going to be head dim by, or sorry, let me repeat that again. Let me rewrite this. So this is going to be batch by heads by sequence len by embed dim. So every single one of these vectors or matrices have been turned into that. And what we're doing now is taking the k, which is batch by head by sequence by embed, and reshaping it. So batch and head stay the same, 0 and 1, but we flip these last two dimensions. It becomes embed by sequence, right? So we end up with we're going to end up doing the map mul between standard attention stuff. So it'll be the map mul between these two things, but this will be embed by sequence. So we're going to be doing a parallelization over the batch and head dimension, which Cupy will automatically do in the map mul, which is nice. And we'll be doing basically an S by E map mul with an E by S matrix, right? Nothing crazy. So that'll end us with the final S by S matrix we typically expect for attention computations. And we're going to divide this, right? Math.square root self.headdim, right? Because that's the scaling factor we typically do. Now that we have our scores, we need to do something, and that's our attention masking, right? Before we compute our softmax, we want to make sure we zero out any positions that our attention mask says not to. So our attention mask is going to be in the shape of 1 by 1 by sequence len by sequence len, right? That's basically what it's going to be, and it's going to be the standard top right, trill triangle. So it'll look, if we had, let's say, only 3 positions, then we would have had something like this. So it would be 0, negative infinity, 0, 0, negative infinity. And lastly, the last one will just be 0, 0, 0. So it's our standard, top right triangle. So I have negative infinity in all the positions that I don't want to compute gradients on, or all the positions I don't want to attend to. Because when I take a softmax, the infinity positions will become 0. And in the way you typically do it in PyTorch, or one of the ways you can do it, is you do a masked fill, right? You basically take the scores and you fill them with negative infinity in these positions. I then want to implement masked fill, so we can just add them in. So we can do if attention, let's do self.attention mask, attention mask is equal to attention mask, and we can do if self.attention mask is not none, I think we actually passed it in, then we're going to do scores plus equals self.attention mask. So we're basically going to take our scores and just add negative infinity to all the positions that we want to be negative infinity, and that's good enough, right? So masked fill basically takes the matrix and indexes it and replaces values with negative infinity. I'm just adding negative infinity to everything because it's the same thing. It makes no difference. And we store the attention mask here because in the forward pass, we want to make sure we don't want to compute attention on any values that are after our current position, right? Because that would break causality. But in the same for the same reason, in the backward pass, we're also going to make sure we don't compute or get gradients from future positions. So we're going to zero those out as well. So here we go. That's everything we need. Good. So now we can do finally our scores reshaped. So remember just like we did our softmax function that we've written so far expects basically it expects a 3-dimensional thing, like batch by sequence by embedding dim. That's the way we wrote it here. And so just to make sure we use that, we want to make sure this is all correct. So we can do our scores.reshape batch size times self.numHeads, and then sequence len by sequence len. So we're going to go ahead and flatten these 2 dimensions. And we have these 2 dimensions here, and it's along this last dimension we want to compute softmax, right? We want to compute softmax along every row of our scores matrix. Okay, so we're going to do probs is equal to self.softmax.forward scores reshaped. And now that we have that, we can do probs is equal to, again, we're just going to reshape it back to how we need it. Probs is equal to probs, and this will be batch size by heads by sequence len by sequence len. So we just have to do these shaping things. PyTorch will do all of this stuff automatically for you, and things we'll write later will do it for you. But for now, we just have to keep an eye on the shapes just so we don't pass something in, because we wrote linear and softmax to kind of expect specific shapes, right? So we want to make sure we keep to those. And now, because we're going to need all this stuff, we're going to store self.probs is probs, self.q is q, self.k is k, and self.v is v. We're going to need all of this stuff for the backward pass. We're going to store it right here. And then we're going to do attention. It's going to be cp.matmul, our probs, and v, right? That's right here. So we computed our probability. So we've done everything, right? We took x, computed all of our projections. We then did qk transpose. We divided by a scaling factor, basically our temperature. We have our softmax. We did our softmax. And then now we're doing the p times v, or matmul, p and v. And so attention is going to be attention.transpose. It's time to put it back, right? So this right now is in the shape of like what we had it as. It'll be batch by heads by sequence len by embedding dim, right? And it's not embedding dim, but it's head dim, right? Head dim. So these should all be, instead of E, these should all be head dim, right? Just so it's clear, right? Head dimension. So we just want to put the head and head dimension back together, and that'll bring us back to E, right? So we're going to go and transpose it. So dot transpose 0, 2, 1, 3. So that's 0, 2, 1, 3. So that puts head and head dimension back together next to each other. And because they're next to each other, we can now do dot reshape batch size by sequence len by self dot embed dim. That'll go ahead and flatten the head and head dimension back into the single embedding dimension. And attention flat is going to be equal to attention dot reshape batch size times sequence len and self dot embed dim, right? Because remember, we're going to pass this through one more linear layer right here. And this linear layer, again, only expects 2 dimensions. So we're going to flatten these 2 dimensions and just pass it in here. And we're going to now get our out is going to be self.out linear.forward, attention flat. And we can now do out is finally out.reshape, batch size, sequence len, self.embed dim. And we return out. So this is our standard forward propagation for a attention, right? For multi-head attention. Not all that different. And what's cool about PyTorch is when you do all of this stuff, it will automatically do the back propagation for you, right? That's what makes PyTorch so powerful. In our case, we need to manually define the back propagation. Luckily, it's not too hard. Just a little bit of care has to be taken. So we're going to get some output grad. And remember, our output grad, right, is going to come in the same shape as the output, right? It's going to be batch size by sequence len by embed dim is equal to output grad dot shape. Our data is going to come in this way. And so what we're going to do is this. Let's kind of look at it from here and take it step by step. We have some grad that's going to come through right here, which means this gradient has 2 ways to go. One is this direction towards the softmax, and one is this direction towards the V. So V is something I want, right? DLDV, right? DLDV is a derivative I need because I need to update, right? I need to get to V so I can get to WV and BV, the actual parameters I need to update. So DLDV is something I need to compute. Well, if O is P times V, then DLDV is just P transpose DLDO. This is exactly what we had done earlier, right? When we were doing the linear layers, right? When we did Y is equal to XW, and we had the B, but bias, but forget that. Then DL DV, so this will be DLDW, was going to be X transpose DL dy, right? Like this is exactly what we had done earlier, right? This is just a state. It's just just because we did it for a linear layer doesn't mean it doesn't hold for everything else. Every matmul works out the same way, and so yes, so we have DL dv. It's going to be just P transpose DL DO, right? DL DO, and DL DO is this right here. This is DL DO, our upstream gradient up to O. So let's go ahead and do that first. This is our DL DO, right? Output grad. Okay, so we need to first do output grad flat, because all the stuff we've done, like the linear layer, so actually before we even get to V, we have to, let's just kind of go back in order. We had this stuff first, this linear layer, this final output linear layer. We need to backpropagate through this output linear layer. So let's start with that. Our output grad flat here is just it's in this shape here, but our linear layer processed the data in batch time sequence length by embedding, right? It was 2-dimensional. So we need to flatten our gradients here as well for the same reason, right? Just to make sure everything is the same. And so we're going to do outputGrad.reshape. It's going to be batch size times sequence length by self.embedding. There we go. And then we're going to do grad attention flat is equal to self.outLinear.backward output grad flat. So I am using, because I already defined it, I know what the backward pass of a linear layer is, because I already defined it. So all I'm doing is I'm taking that output grad and I'm passing it in here, so my linear layer can run its own backward pass, right? So I'm leveraging the backward pass that I've already defined, just to make my life simpler. I mean, of course I could do it all here, but it's more modular this way, right? So we have it. We already have this method, so why not leverage it? So this is going to go ahead and backward pass through the linear layer. So let's go back right here. It's going to take the gradient DLDO and output, basically the output of the, it's going to return my output grad. So if we go back right here, technically, just to make this as accurate as possible, this doesn't go to the loss. This O goes to out linear, which then goes to the loss. So what we've just done is this pass right here, right? DL, D out linear. And this is going to produce some output gradient, which then I'm going to pass here, which will produce a new output gradient. And we're basically going to manually pass our gradient back in the order that we know we did it the forward, right? So we just did this, so we've done the backward in the direction, in the right direction, because this was the last layer we did. So that's the first layer that's going to get the backward pass because it's exactly in reverse, right? And so that's our setup. And so now we're going to do grad attention is going to be grad attention flat dot reshape batch size by sequence len by self dot num heads by self dot head dim, right? Because our backward pass here expected our data in our gradients, I guess, in the 2 dimensions. But now as we keep going back, right, all of this stuff here, notice that there's more dimensions, right? We have more dimensions. So we need to make sure we actually add those dimensions in. So we're going to take the grad attention and add in the head dim, number of heads, and the head dim, which puts us right here, right here, where we had number of heads by head dim was the original shape of this data, right? And so now let's go ahead and, and we have to do dot transpose. And we need to make sure it's 0, 2, 1, 3, right? 0, 2, 1, 3. So that will make our gradients in the shape of batch by num heads by sequence len by embed dim, exactly what I had right here, right? So we're just working our way back. That's what the output of the attention was. It was in this shape. So that's the shape we're going to put it in now. Now we need to do our backward through the attention prob. So let me just copy this line right here. Right, so we need to backward through attention is probs at v. That's this line right here. The output, right, like I mentioned, this attention was in this shape, right? We transposed the gradients to the correct shape, so we're good to go there. But now, like we mentioned before, if y is xw, then dl dw is x transpose dl dy, and dl dx is dl dy w transpose. That's the standard formula for our matmuls, right? For the derivative of these matrix multiplications. So in the same way, we have attention is probs at v. So that means d attention, or I guess dl d probs, right, is the same as writing dl dx. It's going to be the upstream gradient times v transpose. And then dl dv is going to be probs transpose times those upstream gradients. So let's just go ahead and do the first one. We're going to do grad probs is equal to cp.matmul. It's going to be the grad attention and self.v.transpose 0, 1, 3, 2. So what have we done here? Our probs, grad probs, is the same as taking the derivative with respect to x. So that's going to be our upstream gradient times, or matmul, with the transpose of my w, which in this case is v. So that's here. We go ahead and transpose those last 2 dimensions. And in the same way, my grad v is going to be cp.matmul, and now it's going to be self.probs.transpose 0, 1, 3, 2, and then grad attention, right? The other way. And that's my grad v. So that's it, right? Nothing crazy, right? Just trying to make this as simple as possible. This is, remember, grad attention is in the shape of batch by heads by sequence len by head dim. And we map mold it with v transpose, right? And v is already in the shape of batch by sequence len by batch by num heads by sequence len by head dim, but we transpose them so it's head dim by sequence len. And there we go, right? So these two dimensions mesh. So this ends up being an S by S matrix for my grad probs. And there we go, right? So we just repeat everything over and over again. Nothing too crazy, because my probs, remember the probs here, grad probs, is in the shape of sequence by sequence, right? Probs is in the shape of sequence by sequence. So my gradients must also be in the shape of sequence by sequence. So we can make this as clear as possible. And there we go. Those are my gradients with respect to the probabilities. My V's are in the shape of batch by head by head dim by, or actually batch by head by sequence length by head dim. So let's just check this out. Our probs transpose is going to be this. It's S by S, so if we transpose it, it stays the same shape, but we transpose that matrix, so that's fine. And we map mold this with our grad attention, right? So we have S by S, S by HD, and so this will give me a final S by HD, which is the shape of my grad V, which is the shape of my V, right? My values. So we're good to go. And so now that we have all of that, we can go ahead and keep going. First, we have our grad. We'll actually propagate. So, okay, so just to make it clear, we computed DLDV, but we haven't propagated it like more back. We'll do that later, right? We'll keep that later. Keep that for later. For now, let's just go down this path, right? We need to now backprop through our softmax. So that means we have to go through the probs path, right? So grad probs already is our kind of path in this direction. We just need to keep going to get through the rest of this stuff to get to Q and B, right? So let's go ahead and do that. So we're going to grad probs reshaped is equal to, and why are we reshaping it? Because we reshaped it right here. When we did the backprop through softmax, we put in the shape of batch by num heads by batch times num heads by sequence len by sequence len. So let's just put it exactly in that same shape. It's going to be grad probs dot reshape batch size times self dot num heads by sequence len, just like that. That's my grad probs reshaped. And that puts me back in this shape right here, and I can keep going. I also have my grad scores reshaped. It's going to be self.softmax.backward grad probs reshape. So this is me taking my probs right here, right here, and doing, I did a forward pass in the softmax here, so I need to do the backward pass to go back, right? So now I've gone from probs back to my scores, right? These scores, the pre-softmaxed values. Good. So now that we're there, we need to flatten it back. So we're going to, or not flatten, we're going to reshape it back. So grad scores is going to be equal to grad scores reshaped dot reshape batch size by self dot num heads by sequence len by sequence len. That is my current grad scores. Now here's the important part. Whatever these grad scores are, anything that was negative infinity in the forward pass cannot contribute to the gradient in the backward pass. So in the sequence by sequence length matrix, we want to make sure that we zero out any future values, right? And this is what, if we had done a, what do you call it? The masked fill. Masked fill does exactly that. For values that we populate with masked fill, it zeroes them out in the backward path. It does that automatically for us. Or if we had Autograd, we just added infinity, and so in the backward path, it would have automatically zeroed things out for us. We don't have Autograd or masked fill, so we just need to do it ourselves, right? So we can do that real quick. So we're going to do if self.attention mask is not none, right? So if it's not none, then we're going to do grad scores is equal to cp.where, and wherever our self.attention mask was equal to negative cp.infinity, we're going to fill with 0 inside our grad scores, right? So just go ahead and any gradients of those future values, 0 them out because they play no contribution. And masked, if we actually implemented a masked fill method, it would have done this for us, but it's easier if we just do it this way, right? So that's what we're doing. Good. Oh, my bad. All right, up next. Now that we've gone through the softmax and we've also done the mask, we've dealt with the masking, which is kind of all in here. We divided by the square root of epsilon, right? So we divided by, or not epsilon, square root of e. That's just dividing by a constant. So if we divided by a constant in the forward pass, we need to make sure we divide by the same constant in the backward pass, right? This is like saying if y is equal to x over a, then dy dx is 1 over a, right? So we want to make sure we multiply by that 1 over a as we keep going through our stream of gradients, right? Keep propagating back. So we're going to do grad scores divided equal to, in place, math dot square root, again, self dot head dim, just like that. Nothing crazy. All right, good. So now that we're here, we've dealt with this, right? And there's nothing here, so we don't have to worry about it. We're now here. S, our S tilde, is going to be our QK transpose. So what is the derivative of S tilde with respect to Q and S tilde with respect to K transpose? Well, it's the same matmul rule that we've done already. So DL dk transpose is going to be Q transpose DL ds. Now, why is that? Because if we had done DL dk, right? Remember, we want our gradients in the shape of K transpose. We need to basically transpose it. So either we do it now or we do it later. So typically, DL dk would have been Q transpose DL ds by our standard matmul, right? For the same reason we had this here, same reason we did all the, let's go back to the linear layer. Same reason for our linear layer right here. DL, if we had y equals xw, DL dw is x transpose DL dy, right? So for the same reason, we're just doing the same thing because matmuls never change. The reason it looks flipped though, so let's go back. The reason it looks flipped is because we have this extra transpose right here, right? We want DL dk, but we matmuled with a K transpose instead. So DL dk transpose is Q transpose DL ds tilde, just like normal. But if we want DL dk, which is just the transpose of DL dk transpose, because remember, these gradients have to be in the same shape as the tensor we're working on, then we just need to make sure we actually transpose our data correctly. So this will be, DL dk will be just Q transpose, DL ds tilde transpose, and we know that if we have AB transpose, that's the same as B transpose, A transpose, right? So it's going to be DL transpose ds Q. And so that's just a little bit of a numerical, not even just a matrix like trick. Either we can just do it this way and do it correctly, or we can just do it this way here and then just transpose it again. But let's just keep it simple and do it this way. So this step 1 is going to be doing our grad K. So we want grad K, not K transpose. And that's why it seems a little bit different, like flipped from what we had looked at earlier. So this is going to be grad K is going to be cp.matmul, and it's going to be grad scores dot transpose 0, 1, 3, 2, right? We're going to go ahead and do the grad scores transpose matmul with Q, right? So it's going to be self.q. And grad Q is going to be cp.matmul. This one's a little bit easier. It's just going to be DL dq. It's going to be DL ds K transpose, but K transpose was already transpose. So it's actually K transpose transpose, which is just back to K, right? So that transpose makes it a little bit trickier. We just have that extra flip in there, but it doesn't change anything, right? So we can just add that in. So it's going to be just grad scores self dot K. And just to make it clear, let me just put this line right here, right? DL dq is just DL ds K transpose transpose. So that's just DL ds K. And then over here, for the first term, dl dk transpose is q transpose dl ds, right? That's how we normally would do it, but we don't really want dl dk transpose. We want dl dk, right? Because our data is k, not k transpose. We just transpose it for the map mul. So if we want dl dk, then just go ahead and transpose all of this, which just gives us exactly what we had done here, right? Just, okay, good. So nothing too crazy, just small details. But now that we're here, we now have dldq, we have dldk, and we have dldv, right? So we have all the pieces in place for our operations. And so now what we need to do is grad q is currently, we need our, okay, so we need all of our data, or all of our gradients need to be in the same shape as the actual data. Our q, k, and v are in the shape of batch by sequence length by embed dim, right? Not all of this. So we need to just go ahead and place everything back. So this is, let's look up here. Basically, we're gonna undo these steps here, right? Undo these steps here. We wanna, our data is currently in this shape right now, batch by head by sequence length by head dim. We wanna put it back as batch by sequence length by num heads by embed dim. So let's go ahead and do that. I'll just copy these lines in because they're just a repetition. Right, so we're going to go ahead and transpose it, put it back how we found it, and make it batch by sequence length by embed dim. But of course, our linear layers expect these two dimensions to be together because we need 2 dimensions in those linear layers. So we will, one more time, flatten them, right? Flatten them. So we're going to do grad flat is going to be grad q dot reshape batch time sequence by embed dim, right? No problem there. And now that I have everything ready for dq, dk, dv, I can go ahead and backprop through the 3 different linear layers that correspond to them, right? And so to do that, very simply, all we need to do is this. So we have grad queries, grad keys, grad values, and there we go. We're now using the backward pass of the 3 different linear layers right here, and we're basically done, right? So again, once the backward pass is done, they're going to all output their own grads, and we want to make sure we reshape them back to batch by sequence length by embed dim because that's the actual shape of the data. We were just doing this because our linear layer expects it that way. That's all. So we're good to go. We now have all of this. Now remember, x is the thing that created q, k, and v. That means all gradients from q, k, and v, so dq, dk, and dv, need to sum together, right? They all contributed, so we sum all those contributions together. And so the final gradient that outputs out of this attention mechanism will be return grad query plus grad key plus grad value. And there we go. That is our full attention mechanism where we define both the forward and the backward pass, right? Nothing too crazy. There isn't too much going on in here, right? So, which is good. But of course, we want to be as careful as possible. I'd recommend, so if you go through this line by line, you'll see basically every one of these lines is going in the reverse direction of these lines. We're just undoing them one step at a time, and we're just keeping an eye on the shapes because our linear layers are a little bit annoying because we implemented them in the simplest way possible. It would have been ideal to handle this reshaping and all of that inside the linear layer, but I want to keep this as simple as possible, right? So there we go. All right, so that is our multi-head attention. After multi-head attention, we now need our feedforward layer. So we're going to do class ffn grad layer definite. This is going to be much easier. Self embed dim, and dim mult is 4 by default, right? Most transformer models will do that. Self.linear1 is, it is a linear layer with embed dim by embed dim times dim mult. And then self.ReLU, because that's what we're using, is the ReLU activation function that we defined. And then self.linear2 is going to be another linear layer with embed dim times dim mult by embed dim. And so now we're going to def forward self x, and we're just going to pass our data through all of these operations. We're going to do, remember our data's batch size by sequence length by embed dim is x.shape, And so then we're going to do x flat because our linear layer expects flattened data. So x dot reshape batch size times sequence length by embed_dim. And now let's just pass it through our thing. So x flat is equal to self dot linear1 dot forward x. X flat is equal to self dot ReLU dot forward x. X flat is equal to self dot linear2 dot forward x. And now we can just return x back to x flat dot reshape batch size by sequence length by embed_dim, return x. So that's me forward propagating all of my embeddings through all of these linear layers. Simple as that. And now what we need to do is the backward pass. Def backward self output grad. Should be pretty straightforward, right? So we're going to do, again, our output grad will be in the same shape, reshape, will be in the same shape as our output. So it'd be like that. So it'll be in the shape, right? Batch size by is equal to output grad dot shape. But of course, our linear layers don't expect it like that. So we're going to do output grad flat is equal to output grad dot reshape batch size by sequence length, or batch size times sequence length by embed_dim. Go ahead and flatten those two dimensions. And now we just do our backward pass. Output grad flat is equal to self dot linear2 output grad flat. And remember, we do linear2 first, and then we do, and this will be dot backward. Should have put that everywhere. Dot backward. Next one's going to be ReLU. Next one's going to be linear1, and we're good to go, right? That's me taking my gradients, passing it through the first linear layer, passing it through the ReLU layer, passing it through the second linear, or I guess passing through the second linear layer, then the ReLU, then the first linear layer, right? In reverse order of what we had done up here. And now that we have done that, we can do grad is equal to output grad flat dot reshape batch size by sequence length by embed_dim. And we can return grad. Very simple, right? That's our standard feedforward layer. And so now let's go ahead and define a transformer block, right? So we're going to do class transformer block. And this will be the last layer of like abstraction that we need just to kind of pull it all together. Def init self embed_dim num heads. We'll have a dropout p. And actually, to be fair, we haven't implemented dropout yet, so we're going to leave this for later. Let's go ahead and implement dropout first, and then we'll come back here, and then we'll do cross entropy. Okay, good. So let's do dropout first. So if we look at our, let me just show you the PyTorch docs for dropout. Dropout's very, very simple. All we do in dropout is we randomly zero out some of the elements in the input tensor with some probability p, right? And they're chosen independently and all that sort of stuff. Now, the thing about the dropout is we actually do one thing. We zero out all of the values in the forward pass randomly, or no, we randomly zero out stuff in the forward pass, but the outputs that are not zeroed out, we scale them by a 1 over 1 minus p. The reason for this is to maintain the variance. If we just like randomly zeroed stuff out in our matrix, the variance of the matrix will drop, right? So by rescaling our other data that wasn't dropped out by 1 over 1 minus p, it seems to help the neural network quite a bit, right? And you can read about some of these details in the actual paper. And so yeah, you can just read those details in the paper, where you can try it with and without it, and you'll see that training seems to be a little bit more stable when you don't do that. This just makes sure that during training time and inference time, the total variance of the tensors don't change all that much, right? Good, so let's just quickly do that. This one's very, very simple. We're gonna do class dropout. Dropout's just an operation. No learnable things. Self, and p is 0. I'm gonna set 0.5 by default, right? Self.p is p, but also self.training equals true. So dropout is something that we want to apply during training, but when we're evaluating, we don't want it. So we have a flag here, and we'll create a thing that'll toggle the flag later. Forward self x if self.training, right? So if we're in training mode, then self.mask is going to be equal to cp.random.rand x.shape greater than or equal to self.p. So this is going to be a random mask. It's going to create a bunch of uniformly sampled values between 0 and 1. And if it's greater than p, we're keeping it. And if it's not greater than p, we're not keeping it. Right? That's it. So we're going to do self.mask is equal to self.mask divided by 1.0 minus self.p. That's our rescaling factor. So anything that we're keeping, we're going to rescale it with this factor to make sure the variance of the tensor doesn't change drastically. And then we're going to make sure self.mask is self.mask dot as type cp.float32. Make sure there's float32 tensors. Otherwise, it'll default to float64 and slow down training considerably. So x times self.mask. Else, if we're not training, we just return x, right? If we're not doing anything, then we just return x and we're done. Good. Okay, good. Yeah, that's basically it. And we can actually add a and self.p greater than 0.0, right? As long as, if there's some probability, then we won't apply it. If there's not, then just do this. Okay. During the backward pass, very simple. Backward self x if self.training return output grad times self.mask. Oh, this should be output grad and technically we should only ever run the backward pass when we're training, but that's fine. And this is just a multiplication, right? Like we did some like output is equal to mask times our x, right? So if we just multiplied by the mask, then the backpropagation dl dx is dl do dx, and do dx is just m, the mask, right? It's a constant. It's just a constant that we multiplied by. So we just go ahead and multiply our gradients by that and keep it going, right? Nothing, very simple, nothing too crazy here. Okay, and this also has a repr, so we can maybe throw that in there. All right. Okay, now that we have dropout, we can go ahead and build the transformer block. Then we will come back to cross entropy, and then we will do the rest of it. All right, so we're going to do class transformer block. This could be, again, a grad layer, and this is just going to wrap together a lot of the stuff that we've done already. So I'm going to actually copy a bunch of this stuff here because we've already done all this, so we can just paste it here. So we have our MultiHeadAttention, we have our FeedForward layer, we have 2 of those layer normalizations, right, that we defined, and then we have some dropouts, right? That's our standard setup for all this stuff. And so we can do def forward self x attention mask is none in case we don't pass it in, and attention is equal to self.attention.forward x attention mask, right? Just pass it in. And then attention is going to be self.dropout1.forward attention. And then x is equal to x plus attention, and then x is equal to self.norm1.forward x. So I think in GPT actually we should do this line before. I think they pre-norm, but that's fine. In the original transformer, I think they post-norm. So I'm sure I can't remember exactly the benefits of one over the other off the top of my head right now, but that's no problem. We can just keep going. This is just a dummy implementation anyway. So we have here, basically, we compute attention. We did the dropout on attention. Here's our residual connection, right? We add the input to the output, and then we normalize. So there we go. And we're just going to repeat this one more time, like this, right? Then we take the output of this, it goes through the feed-forward layers, goes through another dropout, gets a residual connection, then we normalize one more time. And that's fine, right? So we'll just keep it like this, but technically I think this should be before this here, but that's fine. It's not a big deal for what we're trying to do. Return x, right? So that's our forward pass. Backward pass, again, very, very, very simple. So def backward. So you can see the more of these modules we define, the simpler our backward pass becomes because we can leverage the backward passes we already wrote, to do these things. So our grad is going to be self.norm2.backward output grad, right? So this is the last layer we had. So we want to make sure we just backwards through that layer, right? Nothing too crazy. The next thing we had is this right here. And this is where it becomes a little bit more interesting, because notice that we basically copied, ignore everything on top right now. So ignore all this. We basically had some x right here. We had some x right here. And so this x was added to this right here. So let's maybe draw this out, makes it a little bit clearer. We had some x, and it went through like operation 1, operation 2, and then this produced a new output that x added to this, and it produced like y. And so in our backprop, we have to do two things. We have to first do all the derivatives back to here, but then we also have to do this derivative where we essentially add, right? Because this is just a sum. So we're just going to add the gradient from this direction right here onto the gradient over here, right? Because it's just a simple sum operation. So it's nothing too crazy. Maybe make it a little bit simpler. If y is equal to x plus 2x squared, maybe that's not the right way to do it. Let's do y. Actually, I think graphically it's easiest. Let's just draw that again. We have x. We have op1, op2, and then this has a sum right here. And then this produces a new output. When we do our derivatives, x has two things that are contributing to it. We have contributions of the gradient from here, but we also have contributions of the gradient through here. And remember, we always sum contributions together. So we just need to do that. It's just, in this case, when we're adding things together, right, when we're just doing a sum, then it's pretty easy, because all we want really is do dx. It's just do dx has two chains, and this is basically the total derivative, right, of a thing. There's two ways to get to x. Either we go through this right here, or we go through this top branch right here. And so we're computing the top branch, and then the bottom branch really has nothing in it. So we're just essentially adding or copying the gradients in and accumulating them on x. Nothing too crazy. So this means we need to, let's do the top branch first, right, through all of these operations. Let's get rid of you. Top branch first, so it's going to be grad drop is going to be self.dropout2.backward grad, and then grad feedforward is going to be self.feedforward.backward grad drop, and then grad is going to be equal to grad plus grad ff, right? So this is the gradient that came in through here. And we're just going to make sure we add everything together so we're good to go. So because the residual connection happened here, or before the layer norm, so we're going to do the layer norm, the backward of the layer norm. This produces some grad right here. And then we're going to make sure we do all of these operations here, backpropagate through them. And we're going to add the grad that we produce right here to the grad that came out of the backpropagation of these two operations. And there we go. That's all it is, right? Nothing too crazy. And we're just going to repeat this again, right? So we can just... I'll just copy this in just so I don't have to type it a second time. It's exactly that, right? We have our backward through the layer norm, backward through dropout 2, backward through the feed forward, add those residual gradients together. Again, we have another layer norm, right? Let's group these together. Have another layer norm right here, right? Norm 1. So here we go. Backward through norm 1, backward through dropout 1, backward through attention. And again, we add those residual gradients together, right? In the same way, right? This is our new residual gradient that came out of this norm, right here, and we want to add the gradient of this to the gradients of these things here, and that's right there. Returns our grad. Very, very simple. And this transformer block has a repr, so we can add that in, right, just so we can see it later. Okay, good. And we also now need to do our cross entropy. So this is going to be the last bit of actual math that we need to do, cross entropy loss. This one is fairly short, so this should be okay. All right. So we're going to do two versions of cross entropy, one that's faster and one that's slower. So cross entropy loss, the version we're going to be working on right now is assuming our labels are one hot encoded, just to keep things as simple as possible. So one hot encoded labels basically mean that there's only one correct answer, right? So it'll be 1 at the index of the correct answer and 0 everywhere else, just to keep it simple. We could also implement it for not this, but then we don't get to use some of the tricks that we're about to leverage. And in all problems when it comes to LLMs and stuff like that, this seems good enough. So we're going to do that for now. Okay, so what we're going to do is we have, basically this is our standard cross entropy formula, right? Negative sum over all the classes from class 1 to class n possible classes of yi log pi. Now, the thing is that p is a probability vector, and in our case, p is our probabilities. It was produced by a softmax. So if you remember, in neural networks, we produce some logits, right? So the linear layer produces some values, logits, like L1, L2, L3. This, and let's not use L because that'll get confused with loss. Let's do O1, O2, O3. Those are some logits, some raw outputs in the neural network. We can then apply them to softmax, so we get probability 1, probability 2, probability 3, and then we can compute our loss. So these probabilities are right here. So the first cross entropy we're looking at assumes that our vector that we're passing in is a probability, and that's exactly the limitation of this method, and we'll see why later. But either way, we have our p of I, no problem. So p is a probability, softmax, but y is one hot. It's 1 for the correct class and 0 everywhere else. So technically, p log py is just negative 0 log p1 plus 0 log 2 plus, in case, assuming that this is the correct answer, the second index, then it'll be 1 log p3 plus 0 log p4 plus 0 log p5. So everything is 0. All we're left with is negative log p3. And our goal is to either maximize the log likelihood of this probability or minimize the negative of it, right? Because that's essentially the interpretation. So dl dpi is just minus yi over pi. And this yi is 0 if it's not correct, or negative 1 over pi if it is correct, right? If it is correct. So that's easy enough, right? Let's go ahead and implement that, right? So we just have negative yi over pi. And we'll talk about this limitation in a second. So we're going to do class. This is going to be slow cross entropy loss operation. This is just going to have a forward, and it's going to get a y true and a y pred, right? And just to make it clear, right? This will be the shape. So y true will be just a vector of integers indicating which is the correct answer, and then y pred is just our matrix of probabilities. For every single sample, we have the probability vector of what it thinks each thing should be. Okay, so we can do self.y true is y true, self.y pred is y pred, and batch size is y, or it'll be y pred dot shape is 0, right? Just look at how many samples we have. And so our correct class probs is going to be y pred cp.arange batch size. So for every single sample in the batch, I want to index out the correct answer, right? So what I'm doing here is basically I have a matrix that looks kind of like this. Let's pretend there's 3 classes. So I have P00, P01, P02, P10, P11, P12, P20, P21, P22. Right? That's what I have. That's my matrix. And for basically, this is sample 1, sample 2, sample 3. So it's a batch size of 3. We have 3 things in each thing. And all I'm doing is for every single index, so this is the cp.arange, cp.arange right here is basically saying 0, 1, 2. And I have class labels. I know let's say the correct thing on the first thing was 2, the correct thing on the second thing was 0, and the correct thing on the third thing was 0. So I'm basically saying I want for every single batch, every single sample in the batch, at index 0, I want 2. At index 1, I want 0. At index 2, I want 0. So I'm just indexing out the probabilities of the correct answer. Because in the end, that's what I want to maximize, right? Or minimize the negative log likelihood of those things. So how this is going to work out then is it's going to be loss. So we've indexed them out. And so now we just need to average them together. So loss is equal to negative cp.mean, cp.log correct class probs, and we're going to do plus 1e minus 12, right? Just so we don't take the log of 0 or something like that. And there we go. That's our setup, right? That's the loss. That's the thing we want to minimize the negative log likelihood of. And we can return the loss. Now the backward method is going to be self. Notice that there is no upstream grad because this is the loss function. There's nothing after the loss, right? This is the last thing. So it's just 1, right? That's all it is. The upstream grad is just 1. So this is going to be the shape of batch size by num classes is equal to self.ypred.shape, just so we have that information, size. And like we just saw, we have grad is equal to cp.zeros like self.ypred, right? We're going to make sure the input of this thing was ypred. So the output has to be in the same shape as ypred. The gradients have to be the same shape as ypred. And what we're going to do is grad cp.arange, again, batch size by self.yTrue is equal to negative 1 over self. And let's put this in parentheses, self.ypred cp.arange batch size self.y true. So where did this come from? Again, remind yourselves. Our derivative is 0 for all the incorrect answers. The gradient is 0 for all the incorrect answers, and negative 1 over pi for the correct answer, right? For the correct answer. And so that's exactly what I've done. I've copied into the positions of for every single sample, in the positions of the correct answer, I've copied in the predicted probabilities of those correct answers. And that's it. And actually, yeah, so yeah, we have a, just so we don't divide by 0 by accident, right? And that's it, right? That's the entire gradient. And again, this just assumes that y true are already probabilities, right? That's the important part. And we can return grad. And now let's talk about the limitation here. The limitation is we assumed that the input to our loss function, cross entropy, is already softmax, which means when we do backprop, we have 2 things we need to do. We need to go loss to softmax, and then we need to go softmax to logits. The logits are the thing that we softmax that were then passed into the loss. So when we backprop, we have to go through all of this. And we can technically save one of these steps. We can save one of these steps by just having our backprop just go straight from loss to logits, right? It would be ideal and convenient if it was that way. And this is why PyTorch's cross entropy loss already, cross entropy loss expects logits. The reason it expects logits is exactly for that reason. It expects logits because it will do what we're about to do. And this actually ends up being way, way simpler. So yeah, problem. The previous derivation expects already softmax outputs, which means in the backward pass, we need to backprop through the softmax. So can we avoid that? Let's kind of remind ourselves what's going on. Cross entropy is this. This is our cross entropy formula. And we know this is one hot, right? One hot encoded vector. So it's only 1 for the thing we care about, for the correct answer, and 0 for everything else. And we know that P is this, right? This is our formula for the softmax. So can we just simplify this a little bit? So what I've done, or what we typically do is we write here cross entropy is negative log of P label. Because remember, if we're not P label, I'm going to say P label is the correct answer. Everything else here was 0, right? So only negative log P label survives, and everything else is zeroed out. Okay, if I have that negative log P label, then negative log of my, I can just plug it in, right? What is the probability of label? Well, it's e to the power x label divided by sum of I e to the xi. So e to the x label, sum e to the xi, standard setup. And this is just the log of a fraction, so I can just write that as negative log of the numerator minus log of the denominator. Okay, that's no problem. And we can then do a little bit of simplification, right? We can do log of, where are we looking at? Here we go. So I just rewrite it. So this negative can distribute, right? We can this one becomes a positive, this one becomes a negative. So we have log of the sum e to the xi minus log e to the x label, but log of e to the something is just the something, right? So it's really just this, log sum e to the xi minus x label, and that's it. And now what we want to do is take the derivative of this thing. Okay, let's go and take the derivative, dl dxj, right? Derivative with respect to some xj. Remember, there's xi is one thing, xj is the thing we want, so there's some, because there's so many, a single xj is contributed to by all these different xi's, so we have to make sure we do it that way, just like we did for softmax. Nothing new has happened. dl dxj of log of sum exi minus x label. Well, like we saw before, this is kind of going to be the derivative of a log of something is just 1 over that thing times the derivative of the inside minus the derivative of the derivative of x label with respect to xj is 1 if we have the correct answer, j equals label, and 0 otherwise. Okay, that's fine. And what's the derivative of x e to the xi with respect to xj? Well, this is going to have all the different x1, x2, x3, all the different ones in them, but the xj will only keep the e to the xjth term. So only the e to the xjth term will survive this derivative, and everything else will get zeroed out. So all we're left with is e to the xj over sum e to the xi minus, it'll be, again, 1 if we have the correct answer, and 0 otherwise. Well, what is this? Isn't that just softmax? That is our softmax, right? So our gradient uses the probabilities, and on the correct answers we subtract 1, and on the incorrect answers we just leave it as probability, and that's it. So now our gradient is just probability of j minus delta, or this indicator function, that's 1 if for the correct answer, and 0 otherwise. That makes our life quite a bit simpler. So let's go ahead and implement that, right? Very simple. Class cross entropy loss operation. No init, def forward. And actually, let's go ahead and copy this, because this is identical to the code from earlier. So let's copy up to, actually, yeah, all of this is identical, so we can do that. So what we've done is, first, because we're passing in Logits, we do need to do the softmax. And this is the same numerically stable softmax that we had done earlier in our, we could have also just used our softmax, right? The forward method of the softmax, but that's fine. We have it here. And so we have the softmax outputs. And then what we do is we get the probabilities of the correct class, and then we do the same negative mean log of those correct class probabilities, just like we did earlier, right? Nothing different. It's just now, instead of expecting probabilities being passed in, we are doing the probabilities ourselves, expecting Logits to be passed in, right? Now our backward pass, very simple, def backward, self, and again, there's no output grad here, so we're going to do backsize by num classes is going to be self.logits.shape, and grad is going to be self.probs. I'm going to create a copy of them, and we can do grad cp.arange for every single sample in the batch. For the correct y true, we're just going to subtract 1, because that's exactly what we had done, right? We're doing probability minus our indicator function, where the indicator is 1 when we have the correct answer and 0 otherwise. So for all the positions of the correct answers, we're going to subtract 1, and we can return grad. And that's it. So notice here, we've gone straight from Logits, right? We've gone straight from Logits to the loss, which means when we do our derivative, we go straight from the loss back to the Logits. There's no extra softmax. No extra softmax like we had here that we'd have to backprop through. Now, to be fair, the softmax we wrote is pretty efficient, but anytime, I mean, in real neural networks, we will do these operations hundreds of millions of times for significant models. So any operation we can save on, we should try to save on it, right? And subtracting 1 is quite a bit simpler than, I guess subtracting 1 is technically easier than dividing, right? So fine, we've saved a little bit of effort here, right? All right, and this has a repr. I think that is it for all the layers. So now it's time to, actually no, one more thing. This one's easy. This is going to be FlattenForLLM operation. So this one's easy. Actually, I can just copy it in because it's not even interesting. This is just a thing we need. Remember, when we compute our loss, it expects a batch size by num classes, right? Which in our case is going to be batch size. Okay, it expects batch size by num classes, but our data, the output of the final linear layer, is going to be batch size by sequence len by c num classes, right? So for every single sample in the batch, for every single time step along those samples, we're going to predict what that next character should be, right? Like, what is the next C? And in this case, that's the shape. It's just, we can't, at least the cross entropy we wrote, won't accept this as a shape. So we need to make sure we flatten it. So we're going to do batch time sequence by embed dim. So this will basically be the number of tokens by the num classes. And technically, this shouldn't be embed dim. This should be num classes, but whatever, right? So num classes. And so in the forward pass, we want to make sure we flatten them so our cross entropy is happy. And in the backward pass, we want to make sure we reshape our gradients back to the original batch by sequence length by num class shape, right? So it's good to go. So this is just one little detail that we need for the shapes to again match up, because we are not handling different types of shapes automatically inside these modules, so we have to handle them outside it. That's all. If we wrote better code, it would have been easier, but that's fine. That's what MyTorch will be for later on. Now the most important part, we need the neural net. We need to define the neural network, and the way we're going to do this will be it'll be kind of close to how Keras actually does it, right? We just add a bunch of layers onto our base model, right? So let's go ahead and define a neural network. Self.layers is an empty list, right? And we want the ability to add layers, so self layer, where if we provided a layer, it'll just self.layers dot append layer, and def call self input. This will automatically do self dot forward input. Now we have to write the forward method, so def forward self input. And in our case, we're also going to have the attention mask set to as default is none, but we're going to have the attention mask that we can pass in. And basically our forward propagation is easy. We're going to loop through every single layer, and we're going to use the forward method that we wrote for those layers. So we're going to do for layer in self.layers. We're going to do a quick check here. If is instance, if the layer is a transformer block, then our input is going to be layer.forward input and the attention mask, right? The transformer blocks expect the attention mask. Otherwise, the input is just layer.forward input, right? So only the transformer blocks have the extra, like, you know, the attention masking and all that, but all the other layers don't have any of that, so we're good to go. And we can return input, right? All right, good. Yeah, that should be fine. Okay, so that's our forward. Similarly, we have our backward. Def backward self output grad, and we're going to do for layer in reversed self.layers output grad is equal to layer.backward output grad, right? So basically the way this is going to look is we're going to pass some input to our neural network, and it's going to produce some output. And then we're going to take that output and pass it to our loss. Then we're going to call loss.backward. That's going to produce the gradient of the loss with respect to the output of the neural network. And then we're going to pass that gradient into our model. So when you do Autograd, it's kind of all one homogeneous, like you just call one dot backward, but we're going to have to do two of them. One backward for our loss function and one backward for our neural network here, just to keep things simple, right? Just so you'll see how it all comes together in a bit. So there we go. We're going to go ahead and just kind of iteratively go through every single layer in order, you know, in reverse order, and just pass, you know, do our backward methods. All right, now for some housekeeping. So def parameters, self params. This will be for our optimizer that we still haven't written, but we'll get there. For layer in self.layers. So for every single layer, we're going to do if is instance layer grad layer. So if it's a grad layer, right? Only for grad layers. Because remember, we have two types of layers that we've defined. We have grad tensors and we have grad layers. Grad layers contain parameters, right? Grad layers contain tensors. So that's the important part. So we are going to call the parameters method here in the grad layer, which will give us access to either the grad tensors inside them. So like in a linear layer, the grad tensors would be weight and bias, right? If the bias is there. But we also have modules on modules. So that would be, for example, our MultiHeadAttention is a grad layer, which contains more grad layers. So it needs to recursively search, go through all of the, so this grad layer is going to access this grad layer, and then inside this grad layer, we have grad tensors, right? So that's why this dot parameters up here, all the way up, this dot parameter here checks. If it's a grad tensor, then we're good to go. That's a parameter. If it's a grad layer, then use the dot parameters again on that grad layer. So that would, recursively access dot parameters, and then it'll check again. And inside like our MultiHeadAttention, we'll have a linear layer. And then the linear layer, if we call this, it'll have tensors inside them, right? So it just needs to check all of them. Okay, good. So that kind of handles a little bit of that annoyance for us. So as long as it's a grad layer, right, then it'll be layer parameters is equal to layer.parameters and params.extend layer parameters. Return params. I think I got that. So for layer, self.instance, grad layer, yeah, just grab the parameters of that layer and then just add them onto our list of all the parameters that we have, right? Good. Now we need to do our two things. We do have a dropout, so we need to make sure our model can be set to training and evaluation mode. So that's easy. Self.train is true, right? Self.training is true. And we're going to do for layer in self.layers. In self.layers, we're going to write a method called self.setModeRecursive layer true. Let's write that method. Def set mode recursive self layer mode. So basically we need to recursively go through all of our modules because again, the MultiHeadAttention grad layer doesn't have a self.training, but the FFN, the feedforward network, if we recursively go into the, if we recursively go into the dropout layer, then the dropout does have it. So you can imagine, like, for example, here, let's maybe make these all small so it's easy to show, because I think this part is good. Then dropout. Okay, good. So for example, this transformer block contains MultiHeadAttention and feedforward. So we need to recursively go check in these. And then these things, FFN does have a dropout, right? It does have a dropout right here. So we want to use that. We want to toggle that. So we just need to recursively search through all the layers, and that's easy enough to do, right? We can just write a method that does that. We're going to do if has adder self.training, which in our case, the only thing with self.training will be the dropout layer. Self.training is equal to mode. And we can do if is instance. So like if it's anything else, if the layer is an instance of a grad layer or an operation, right? Either thing is valid. Then we can do for adder name, adder value, and layer dot. Just go ahead and check through all of the different, things that are saved inside this specific class. We can do if is instance adder value. Grad layer operation self dot again set mode recursive adder value mode, right? So all we're doing is if the thing is a grad layer or operation, then go ahead and check inside it. If inside this, mostly just for grad layer, if inside this grad layer we have another grad layer or other operations, then check inside those. And this is just going to recursively check all of them, right? Nothing too crazy. So now we can set an evaluation. We can do self.training as false, and we can do for layer and self.layers. We can do self.set mode recursive layer false. right? So there we go. This will basically loop through all the layers, and within each layer, recursively check through all of the grad layers and operations to see if the self.training flag exists. If it does exist, set it to the mode that we want, true or false. And if it doesn't exist, but it contains more grad layers or operations, then keep checking. Just go through all of them until we exhaust it, right? Nothing too crazy. We also need the ability to save and load parameters, so we can do that. Def save self. I'm gonna just give it a file path, and we can do params dict. It's an empty list, and we can do for I param and enumerate self.parameters. Right, so we're going to loop through all of our parameters, and we can just do params f param I. This is a really bad way of doing it. We should actually have actual, PyTorch gives each parameter an actual name, so you know exactly where it goes. I'm just going to index it, and this assumes that you load the model exactly the same way you trained it, but that's fine. This is not supposed to be something too intense, just to keep things simple. And what we're going to do is when we save our parameters, we need to make sure they're actually, so all of our parameters by default, notice that we've done cp.everything. They're all GPU tensors. We need to make sure they are NumPy arrays for us to save it, right? So we're going to do cp.as NumPy params param.params, right? This is basically going to copy into our dictionary our parameters as a NumPy, basically a CPU tensor, right? Move from the GPU to the CPU. And we can do np.save the file path, and we can just unpack the params dict and pass it in, right? And that's it. That's just going to go ahead and save it. Def load self file path, and we can do if not path. And here, I'll just copy this in because this isn't that interesting. It's just a sanity check. Right, so we're going to check. I need to import OS. Let's do that. Just make sure that the file actually exists. We can do that right here. If it does exist, use NumPy to load it, loop through all of our parameters, grab the specific key of the thing, and then load it in. And this is a terrible way of doing it because if there's a mismatch, or if you redefine the model or something, it could mess it up, but that's okay. We're not dealing with exceptions today. We're just going for simple, and it should be okay. And then lastly, def repr. We want to be able to print out our model, so we're going to do model repr is, let's call it neural network, and just put a new line character at the front, so it'll go, and then we can loop through all of our layers. So we can do for layer in self.layers. We can do model repr plus equals f. We can do a tab, or not a tab, let's do 2 spaces. And we can do repr layer. Just grab the exact name of the layer, add a new line, and then at the end, model repr plus equals, and parenthesis, return model repr. That's just going to go ahead and print a model, so we can see what the model looks like after we define it. All right, time for moment of truth. So let's go ahead and write a quick training script. At this point, it's going to be pretty close to the min-GPT implementation from Karpathy. That was the entire intention of this, to basically do a tiny GPT model on Shakespeare data with no PyTorch at all, because we've defined everything here on our own. But yeah, so let's go ahead and let's see, what do we need to do next? Let's define our model next. Good. So let's go to model. We're going to do from data classes, import data class, and we're going to do from import nn. So we're going to do at data class, and we're going to do class GPT2 config. And it's going to be a tiny little GPT. So we can actually just copy this config in, right? So we're going to do the vocab size. We'll have 65 tokens in it, or 65 possible tokens. It's a character level model. We'll have a 380 for embed dim, 6 heads, 6 layers, dim multi 4, dropout p of 0.1, and a max sequence line of 256, just to match the implementation from the min-GPT, right? To keep things similar. Def get GPT2. And so this is where we'll actually build the model, right? So we're going to do model is equal to nn.neural network. And then we're going to do model.add. What's the first thing we need to do? We need embeddings, right? So dot embeddings. Vocab size is going to be config.vocab size. And embedDim is equal to config.embedDim, right? So that's the first thing we need. After we do our embeddings, we need to add positional embeddings, right? That's the next step. So we can do model.add nn.positional embeddings max sequence len equals config.max sequence len. EmbedDim is equal to config.embedDim. So there we go. Now, after our positional embeddings, now we go into our transformer blocks. We're going to do for blank in range config.numLayers. How many transformer blocks do we want to add? Well, however many layers we want in our config, right? And there you go. We're going to loop through, add a bunch of these transformer layers. Oh my god, I can't speak. Model.add. Remember, we need to make sure we flatten. So we're going to do nn.flatten for LLM. This is because we need to make sure that our stuff is flat for cross entropy and all that. And we can do model.add nn.linear. Oh, I guess I do the flatten for, it doesn't actually matter. I could have done this after the linear layer, or I could do it before the linear layer. Linear layer has to be flat for the linear anyway, so I guess this saves me an extra flatten, unflatten operation. But in that case, just to make this as careful as possible, this is technically the EmbedDim, because I'm doing it before I do the linear layer, right? So there we go. That's fine. It doesn't really matter when I do. I just have to do it before the cross entropy, so that's no problem. And so the linear layer is going to be taken in features equals config.embedDim, and we're going to map it to out features equals config.vocab size, and we can return the model, and that'll go ahead and define our actual model. So we can do print get GPT2. Let's do GPT2 config. Let's see what this does. There we go. So it's a neural network with an embedding layer, positional embeddings. We have all of these transformer blocks. We have that flatten, and then the final linear layer to our, our setups, our characters, right? Predictions. Good. That is our model. Let's go ahead and do an optimizer. So we'll write two really quick. We're going to do import Cupy as CP. All right, so we're going to do SGD just to kind of get us warmed up a little bit. So self parameters learning rate, and we're going to do self.parameters is parameters, and self.learning rate is learning rate. So our optimizer needs two things, step and 0 grad. Right? These are the two main methods for an optimizer. And so we can do for param in self.parameters. We're going to loop through all of the parameters. And remember, when we do param, oh, they need a self here. Self here. Okay, good. Okay, so one thing to keep in mind is when we do, and this is just how Python, it's just about Python. When we do this right here, when we do dot parameters right here, neural network dot parameters, these params that we're storing here are not a copy of the parameters of the model. It's the actual, it's just access, right? It's like a view almost, right? It's to the parameters of the model. And because they're a view, if I change the params in this list right here, that'll change it in the entire model, because this is basically just pointing towards the parameters in the actual model, but I can change it inside here rather than going into the model every time to do it. So that's why I can write my optimizer here and loop through the parameters here, update them here, but they're actually updating in the model because these parameters are just a view of those parameters in the model, right? It's just how Python works, right? So we first need a sanity check. We want to assert that param.grad.shape is equal to param.params.shape equal. And remember, when we did the backward pass, every single backward pass, if we look at our linear, for example, what we do is we populate, these are grad tensors, or grad tensors. So in the grad tensor, we had a self.grad, which is set to none. In the backward pass, we take those .grad values and populate them with some gradient information. And so what we're doing now is taking a look at the grad of our, taking a look at the gradient data, taking a look at our actual parameters, just making sure that they're the same shape. If they are the same shape, then we can do param.params minus equals param.grad times self.learning rate, right? Because this is our standard SGD. SGD just takes a step against the gradient, right? Because the gradient will tell you what happens when you increase. We want to decrease, so we want to minimize, and so we're going to do minus equals to, right? Because that minimizes our gradient. And there we go. That's very simply our step, and we scale it by some learning rate, right? Nothing too crazy. And when we want to zero gradients, we just loop through our params for param in self.parameters. We just do param.grad equals none, right? We loop through, set them to none, and we're done. Okay, good. So that's SGD. Of course, we want to implement something a little bit better than SGD, and that'll be the Atom Optimizer. So we will write just an easy version of this today. We'll do Atom W and all that when we do our big bad implementations later. Beta 1 is 0.9. Beta 2 is 0.999. And EPS is, I think, 1e minus 8 by default. I don't know. Okay, I think that's fine. Yeah. So now we're going to self.parameters. I missed a comma. There we go. Self.parameters is param. Let's just call it parameters. So it's the same. Okay, self.learning rate is learning rate. Self.beta 1 is beta 1. Self.beta 2 is beta 2. And then self.EPS, EPS is EPS. There we go. And so how Atom works is instead of just changing our parameters based on the gradients, we instead want to have a moving average, right? Basically like a momentum, right? Like basically a moving average, right? Like an exponential moving average or whatever of our gradients. So what we're going to do is track our gradient history over time. And we're only going to, and basically it smooths out our gradient updates, right? These are momentum-based optimizers. So what we need to do first is create some momentum vectors for each of those parameters. It sounds fancy, it really isn't. So what we're going to do is self.m is going to be cp.zeros, right? Or zeros like p.params for p in parameters. And then self.v is going to be cp.zeros like p.params for p in parameters. There we go. And these are going to be the momentums for the first moment, and these are going to be the momentums for the second moment, right? And then we also have a bias correction. So we're going to do self.t is 0, and we'll see what that looks like in a second. So we're going to do def step. Again, we need a step. Every time we take a step, we're going to update it self.t plus equals 1. Right, we're going to iterate saying we've done a new time step. And this is where our setup happens. So we're going to do we're going to do for I param in enumerate self.parameters. We're going to loop through all of the parameters. And what we're going to do is self.m I, so basically the momentum vector for this one is going to be self.beta1 times the current value, self.m I, plus 1 minus self.beta1 times param.grad. Okay, so what you should see here is basically every step I'm going to do beta 1, like 0.9 times my current history of gradients, plus 1 minus 0.9 of my new gradient. And you can see it's basically going to update as we go. And that's it. That's all that's happening. And the reason this is important is if we have a 0.9, for example, for our beta, if we have a massive, let's say you're training and you have a massive gradient, accidents happen, maybe a floating point error, you'll get a massive gradient right here. But instead of just completely destroying your model, like this, if we get a huge param.grad, that'll completely ruin your parameters and it could destabilize training quickly. Instead here, you might get a massive gradient here, but it will be smoothed out because you're saying I want to basically 90% of the time, 0.9, 90% of the time, I want to leverage my existing history of gradients, but 10% I want to put towards my new gradient. And the higher your beta 1, the more smoothing that happens, right? The more emphasis you place on your new gradients or your existing history of gradients than the new ones. The lower your beta 1, the more dependent you are on your new gradients as opposed to your history. And that's why, that's why like GANs, for example, love using lower beta ones, like 0.5. So your GAN can quickly optimize and adjust, and the generator can quickly react to the discriminator, right? It's not always leveraging its history. So yeah, that's basically it. That's just something to keep in mind. That is our M. V is identical. So M is for our first moment, V is for our second moment. So this will be for our square gradients, right? And this is typically a much higher value. So there we go. Now this requires some bias correction because this is imagine like we're basically doing this one iteration at a time, and this is going to essentially scale as we go. And we want to make sure that as t gets larger and larger, you have more and more history. So we just need to correct for that. So this is just a simple bias correction. We can do bias corrected m is self.mi divided by, and I'll do a whole video maybe on Atom later. I don't want to make this one go on for too long. So this is just a implementation of the algorithm today. So yeah, we're going to just do that, and then bias corrected v is going to be equal to self.vi divided by 1 minus self.beta 2 to the power self.t. So basically you can imagine beta 1 is less than 0.9, or it's less than 1. Right? So as t gets larger and larger, this value is going to get smaller and smaller, like 0.9 squared, 0.9 cubed, 0.9 whatever, and then this is going to get closer and closer and closer to 1. So basically this will be like once we've done enough iterations for t, this whole thing is going to get closer to 1, and then that means this thing is just 1, and really we're just dependent on this. But initially we don't know anything, right? So we have this kind of bias correction right here to help with that. Okay. Now we're going to do params minus equals self.learning rate times bias corrected m divided by cp.square root bias corrected v, and let's put this in parentheses, plus self.eps, and we can then, and that's it, right? And then our zero grad is identical to before. Right? Nothing changed there. And this is, again, this was a little bit quick. I didn't really talk too much about the Atom Optimizer, but that's not exactly the intent of this video, so that's okay. Maybe we'll make a separate one later for that, but that's basically what this algorithm is. We go ahead and we, where are we? Here we go. So we have beta 1 times our current value plus 1 minus beta 1, our new kind of gradient information. We do the same for the square, and then we update in the 1 over 1 minus beta t. There we go. Good. So now that we have all of that ready, we can go ahead and start a training script. And hopefully everything works. I'm sure there's going to be a bug in here somewhere, so we will find it when we do. I'm going to copy a little bit of this in. So this is going to be very close to the MinGPT training script. So this is just a text file that we can load in with requests, just so we can tokenize it and stuff. So cars is going to be sorted list set text. It's going to go ahead and load that text file, and vocab size is going to be len cars, right? How many tokens do we have? And then we just have these two simple things, which I will save right here. So we create a character index, right? Just so we get the mapping, and then index to character. And then we store these tokenizers as pickle files so we can load them during inference time, right? And our data is going to be equal to cp.array. It's going to be one giant array of car to index character for ch in text. We're going to loop through every single letter in our data set and tokenize them, right? Just give it a number that represents them, because this is a character level model. Okay, def get batch data, batch size, sequence len. The index is going to be equal to, so to grab a batch of data, all we're going to do is just grab random samples. We're going to do cp.random.rand int 0 to len data minus sequence len minus 1 batch size. So just grab a bunch of random starting points for our indexes, and our inputs is going to be cp.stack data I to I plus sequence length for I in index. So we're basically going to loop through our data, grab slices of sequence length for however many samples we want in the batch, and then those are inputs. And then our targets will be exactly the same thing. But because we're doing teacher forcing like we normally do for GPT type models, is we want to predict the next token, right? So we're going to do sequence length plus 1. And we can then return inputs, and we're going to do targets dot flatten. Because remember, our loss function that we've written for cross entropy here expects basically our target values to just be a single vector. So we'll flatten it later, but that's basically the main idea. Our target should be one long vector. And so we'll be flattening. Remember, we have our outputs, the Logits, actually will be batched by sequence length by embedding. This will be flattened with that FlattenForLLM by to batch times sequence length, and not embedding characters like possible classes. And so our targets should also be a batch times sequence, right? So that's all we're doing. By default, if we don't do the flatten, this would be batch by sequence, a two-dimensional vector as we're stacking it, two-dimensional matrix of targets that if we don't stack it, but we can go ahead and flatten them and it becomes one long vector of just our targets, right? And that just goes ahead and sets it up for a cross entropy. Okay, and now to train, very, very simple. We can do our config is GPT2 config. I'm just going to use the defaults, so I'm not going to change anything here. And our model is going to be equal to the get GPT2 config, right? There's our model. We need a causal mask, so we can do that. Causal mask is going to be cp.true, right? Upper cp.ones, 1, and then config.max sequence length, config.max sequence length, right? So I just want, basically I want an upper triangle of negative infinities. So we actually need to do that. This is just 1, so we need to do times negative cp.inf, and we're going to do k equals 1, right? So this will just create an upper triangle of our masks, right? Nothing too crazy. And that's what we need to pass in for our thing. And we will, the maximum sequence length that we can support is whatever our config says is the max sequence length. So there we go. Okay. After that, we need a loss function. This will be nn.crossEntropyLoss. We need our optimizer. That's going to be optim.atom model.parameters. Learning rate, we'll just set it to something like that. This should be fine. And we need to make sure, by default, our model should already be in training mode, but that's fine. We can do training iterations is 5,000, and let's do a batch size of 16, whatever, it doesn't matter. Now, training is pretty straightforward. It's just like training any other model. So we're going to do for iter in TQDM range train iterations. We'll do inputs. Targets is get batch data, batch size, and config.max sequence length. So we'll be grabbing, full 256 length sequences, a batch size worth of them from our data set. And everything's already on the GPU because we're using Cupy. So Cupy only works on the GPU, so there's nothing to do there. And so then we can do Logits is equal to model.forward inputs causal mask, right? That's our forward method. We're going to be passing in our inputs in the causal mask. And then we can do our loss. It's going to be the loss function dot forward, right? So this is going to produce some logits, right? Here, what we predict the answer should be. And then our loss function will take y true is the targets, and then logits equals logits, right? That'll be our loss. That'll be the loss. And so now what we can do is loss grad is equal to loss function dot backward, right? This is going to go ahead and compute the derivative of the loss with respect to the output of the model. So that's backward. So this is derivative grad with respect to logits, right? That's the first one. And then we need to do grad of model with respect to logit, right? So basically we need to go one more back. And so now we can do our model dot backward loss grad. And this should be, yeah, loss grad. So there we go. Nothing crazy, nothing crazy. Oh, actually, no, this should be grad of logits, of logits with respect to loss, right? So this is going to be d loss, d logits. And then we're going to do d logits to everything else that's in the model, right? And so that's why there's kind of two steps here. We need to backprop through the loss and then backprop through the model, just because they're two separate things. But that's okay. We'll have a cleaner way of doing this later anyway, so this is fine. Okay, so now that we have that, that computes all of our grad. So now we can do optimizer.step, optimizer.0 grad, and then we can do a quick check for epoch. Let's say every, or not epoch, for iter percent, for if iter percent, I don't know, 500, so every 500 iterations, we can do a quick thing. We can do preds is equal to cp dot argmax axis logits equals axis, or sorry, logits axis equals -1. We're going to go get the last one, and what we're going to do is print the accuracy. We're going to do accuracy. I know accuracy is not a good metric, but that's fine. Is equal to cp.mean preds equal targets times 100. So we're going to see with what accuracy are we predicting the exact target characters, right? So nothing crazy. So there we go. And then we can do our, let's see here. We can throw the model into evaluation mode and then throw the model into training mode again afterwards, so we don't forget that. And we can just do some printing. Let's just generate something to see what it looks like. So we can do cp.array, and we can do car to index. We can pick some starting, like, I don't know, we can do the new line character. Am I missing a... No, I'm good. Yeah. So basically, I'm starting the generation with a new line character just to see what it makes. Or we can pick something else. Like let's pick A. There we go. Letter A, whatever. And we'll just let it generate and see what happens, right? And so we can do generated is going to be just seed.item. So .item is how .item, same thing. It just copies from the GPU a single value to the CPU, right? For Cupy, so nothing changed there. So that's Cupy specific. If you're doing this in Numpy, then you'll have to change that, but that's fine. You can figure that out. And we can then do for blank in range config.max sequence len. Go ahead. We're going to do cur len is seed.shape1. What's the current length that we're at? And we're going to do logits is equal to model.forward. Forward. We're going to pass in the seed. We're going to pass in our causal mask. And we're going to make sure our causal mask is only needed up to the current length, right? We don't need more than that. So we can go ahead and just clip out only the piece that we need. And then our last logits is going to be logits -1. We only need the last one, right? So we don't need any other ones. And now that we have that, we can do probs is equal to cp.exp, and we'll do last logits minus cp.max last logits, and then we can do probs. So we're just doing the softmax here, right? Just standard softmax, so we can sample something. So we can do divided by equal to cp.sum probs. This will give me basically the probability vector of what I think the next token should be with these probabilities. And then I'll just random sample from them. So we can do next token is equal to cp.random.choice vocab size. And it'll be size. We just want to sample one thing. P equals props 0.get.item. So item basically unpacks it out of the array. It's just a single value, and .get is what copies from the GPU to the CPU in an easy way. So there we go. That's our next token. And then we could generate it .append next token, and we can do seed. We have to update the seed, right? So it can be cp.array generated, and we have to do a quick dot reshape 1 minus 1, right? We have to make sure that batch dimension always stays there. Otherwise, none of this would work. We always expect the batch dimension. And we can then do print just with empty, with nothing. We can just join everything together because space is one of our things. And we can do index to car I for I in generated. Did I not call it that? Oh no, I put underscores inside it. There we go. Index to car. All right, and then the model gets thrown back into training mode and it just keeps going. And then at the end, I can just save the model like this. So now let's look for all the bugs. Python train.py. If has adder, expected 2 arguments, got 1. Okay, so this is going to be, let me double check. So we are looking in NN. So this is going to be has adder, which one are we looking at? Self.training. Oh, this should be has adder layer training. My bad, right? So if the layer has the attribute training, which only the dropout layer does. Okay, item, so it should be items. That's true. Well, all the bugs are in here. So items, plural. Sequence len and max sequence len, tuple and int, 187 in forward. All right, let's see. 187. You would be right over here somewhere. 187. Oh, this is not, okay, yeah, okay. I already know this is to be true, so it's fine. I don't need to worry about it. Okay, now for actual indexing issues. So self.wait, so this is in line 188. This is in wait.params. It looks like I have a slicing error. So slice stop must be, let's see here. Self.sequenceLen should not be x.shape, right? It should be x.shape1. There we go. Okay, we're getting closer. We have different Ks. This is going to be cp.matmul. So this is line 68. Let's go over here. So let's print out, let's see here. Print x.shape, self.wait.params.shape. What are we missing here? So we have a mistake in our forward pass somewhere in our feed forward. Looks like it's where it's happening. Okay, so let's go check on our feed forward layer. So we have right here ffn. This should be x flat, x flat, x flat. Otherwise that doesn't work out, right? Okay, making progress. Now we have in our attention mechanism, all right, let's check MultiHeadAttention. In grad q. All right, let's check. So we have grad q right here. Print grad attention dot shape and self dot k dot shape. Oh, I don't think it should be grad attention. 1 second here. From grad, not grad attention, but grad scores. My bad. It should have been the same grad scores as this one right here. That was my bad. All right. How are you doing now? All right, there we go. Now we're off. And so you can see we actually get a reasonably fast model, right? Like it's doing about, I mean, this is about half the speed of what we will be implementing with mixed precision, fused operations, all that sort of stuff. But let's just give it a second here. Let's see if it can generate anything reasonable. It's glad to get to 500. What we're looking for is like evidence of something that looks like English, right? And you can see it's already starting to look a little bit more like English. And that's basically it, right? That is the, and actually, while this is running, we can just go ahead and write a, I'll just copy this inference script in because there's nothing new in it. Inference.py, it's just a copy of the exact existing code. And all I've changed is I'm loading my tokenizer, I'm loading that model. So I wrote the model.save, so now I have the model.load. And all I've really changed is instead of just generating up to 256 characters, I'm going to generate 5,000 characters, but I only have context over the last 256. So my current length is the min of whatever my max sequence length is or how much stuff I've already generated. Because up to 256 tokens, I can have full attention over the sequence. But after 256 tokens, my context length was up to 256. So I basically forget about the older stuff. And that's basically how we can generate things. And you can start to see this is looking a little bit more like English. What would have been helpful actually is to print the loss out so you can see it go down. So let me add that in real quick. So if we go here in the training function, what we want to do is, and I should have done, though I forgot to do, is this right here. And this should be iter, not epoch. Iter. Oh, don't do that. Iteration. And let's make you 100 so it's a little bit more frequent. Okay, good. Yep, so it's off to the races again. So yeah, this is in, let me rename you. Rename inference.py. I also had some, this only takes like 5 minutes to train, so it's not that big of a deal, but that's fine. So yeah, we can see this happening. We see the loss started at 4.2, now it's down to 2.5, 2.50, 2.43, and it'll just keep decreasing. You can see also the accuracy, right? With 30%, 29% accuracy, we can predict the next token, 2.35. So we see the loss, it is indeed decreasing 2.26. So that's good to see, right? It's learning something. And again, remember, this is a full implementation with no PyTorch, no Autograd, no nothing, right? We just rewrote. If you made it this far, great job. But we wrote everything, the forward pass and the backward pass for all of the different operations that we care about. And so instead of waiting, it only takes 3 minutes, so it's not the big deal. We can just quickly run the inference.py. And you're going to see it just starts it's just going to keep generating. And this clearly looks like English, right? It may not mean anything, but that's okay, right? We'll just keep writing junk Shakespeare, which is kind of fun. Either way, this again is the purpose of this was to be a precursor to MyTorch, which is what we'll be getting into in the future. Because MyTorch is a little bit more complicated than what we've done here, but all the fundamentals stay identical. Nothing changes. For example, maybe I can open up MyTorch real quick. So let me open up MyTorch. I'll give you a quick example of how everything we've done today comes back again. So MyTorch is this. It's an active project, so you can already explore it if you want to. But the main thing is this. We have a bunch of operations that we want to support. I'm still working on lots of them. But the main ones, let's look at layer normalization, for example, right? LayerNorm. So if we look at MyTorch, and the purpose of this is to be as easy as possible so you can see exactly how everything fits together. So if you go to MyTorch and then functional, and we look for LayerNorm in here, layer normalization has two options. Either A, we do the layer normalization exactly how we normally do it, right? So we compute the variance, compute the norm, we shift it, we add the bias, all that stuff. We do everything exactly how we normally do it. And PyTorch's Autograd will automatically backpropagate through all of this stuff. But remember, the main penalty for Autograd is that if we do it this way, all of these intermediate outputs have to be stored, they have to be cached, so we can backpropagate through them one at a time. Right? Just adds extra compute that we would like to avoid to do. On the other hand, when we do a normal implementation, this stuff right here is basically copy-paste from what we have already implemented, right? We just go ahead and we compute our means, variance, the inverse standard deviation, go ahead and do our scaling, add everything together, multiply by our gamma, add our bias, and then our backward pass is the backward pass that we've just implemented, right? We had our bias, grad with respect to the weight, right? We had our grad respect to, so that was just some grad output x hat. We had it for the bias, and then we had it for the input, right? And this is the formulation that we just did. Literally copy pasted from what we had done. So this is extremely important because, again, we want to use as many we want to use as many operations as possible where we combine these things together. So because Autograd, as convenient as it is, we typically don't want to use it for known composites of operations, right? If we know exactly what LayerNorm is, we know exactly what the backward pass should be, so why use Autograd when it's cheaper, more efficient to use this? And then, of course, this is all well and good, but something we'll talk about later is every single time we do one of these operations, this is a new kernel launch. Like every time we do one of these operations, this is a new kernel launch. It launches a new kernel on your GPU to do these things. And something that we're going to see is that, like, there's no point. We don't need to launch a bunch of kernels on the same data. I'd rather launch one kernel, do all the work on the GPU, and then come back. And this is why we'll be writing Triton kernels to do exactly the same thing. So if you go to fused ops and then go to, again, a lot of these are a work in progress, but if we look at LayerNorm, for example, we will be doing exactly the same thing. It looks fancy, it looks scary, don't worry about it right now, but it'll be exactly the same forward pass. We're basically going to compute our mean centered, multiplied by the inverse variance, multiplied by our gamma, add our beta, and then return it. And then again, in the backward pass, if we look over here, it's going to be exactly the same thing. So here is that's training. Here we go, backward pass. The backward pass will be identical, right? I mean, it has some scary looking stuff, but we're going to work through all of that later. It's not a big deal. So that's going to be LayerNorm backward. And so here we go. We have exactly that same formulation from before. For the backward pass, we're going to implement it right here. And that's it. So the purpose of MyTorch and everything that we've done is to create a fully functional deep learning framework, at least something that reasonably works. And when I say reasonably works is we can look at this, for example. This is a reproduction of the GPT-2 124 million parameters training on 4 GPUs in mixed precision on the MyTorch system. And we can see we get pretty, I mean, I could probably keep training this. I just lost patience, but it reached a loss of about 2.95, 2.96-ish, which is pretty close to the paper. I think if we got to like 2.9, it would be close, but it would need to train for like another maybe 2 days or so, and I've lost patience, so it's okay. This is mostly just a proof of concept that all of this works. So I hope this made sense, right? So everything we've talked about up till now, it's just a precursor. It's basically the prerequisite to everything that we're going to be doing. We won't be doing manual backwards anymore for a lot of different operations, except for some core ones where we see that there is a speed benefit, right? And like a legitimate benefit to that operation. For example, linear layers are super fast. They're already using cuDNN in the backend, or like cuBLAS in the backend. Like Cupy is already using that. There's really nothing I can do to make that faster for the most part. On the other hand, attention is something that can get very expensive very, very quickly, especially with its quadratic complexity. This is why we'll be implementing a flash attention Triton kernel that does all of the heavy lifting for us, right? It basically makes large attention way more computationally and memory feasible. So there's going to be a lot of stuff that we're going to build up to. Up next will be, I think the figure here gives you a pretty good roadmap. Up next is we need to build a unified array. And this next video on the unified array will be the least interesting thing in the world. So I'm kind of debating if I want to do it or not, or just do a quick kind of run over it. But the unified array is basically just some just management of being able to run NumPy operations on GPU GPU tensors. And this is just class management to homogenize Cupy and Numpy. It's not interesting in any meaningful way. So I'll consider if I want to actually do a full video on this or not. But either way, I hope this made sense. I know it was a long one, but there was a lot of little mathematical things that I really wanted to cover. So I will see y'all in the next one.